Okay. All right. So very good evening all. In the yesterday's session, we have started the new chapter DC to AC converters, and we have already discussed about the single phase half bridge inverter. And regarding the single phase full bridge inverter, we have completed the resistive load. Now let us discuss the single phase full bridge inverter with a purely inductive load. Okay, so pure L load, right? So single phase full bridge inverter with L load, purely inductive load, right? Same circuit diagram. The only thing is in the load branch now we'll be having a inductor here, right? So we're having supply voltage. It is a VS, S1, S2, S3, S4, right? S1, S2. Yes, tomorrow will be the last day of power electronics, right? We'll finish it tomorrow. D1, D4, D3, D2. Inductor L, voltage V0, and current I0, right? The waveforms. Yes, offline classes will be starting from Saturday, 11th, right? V0, so it is like a T by 2. Here it is a T. This voltage is Vs. Okay. I0, the waveform of I0, it is a triangular wave. Okay, it is a triangular wave. This is a linear increasing, linear decreasing. This type of waveform. Same here, minus I0, and this is like a plus I0. This instant is T by 4, T by 2, 3T by 4, and here it is a 2T, right? Here it is a 2T. Okay. Okay, right. So we're having V0, I0 waveform I have drawn. So now let us discuss the circuit operation. Yes. From T by 4 to T by 2, it is like switch S1 conducts. After S1, that is S1, S2. Inductor stores energy. After that, it releases energy through D3, D4. And next here, S3, S4. In the continuous cycle, here it will be D1, D2. Okay. So let us discuss the circuit operation now. So from for very first cycle, it will start from 0 definitely. But for continuous cycle, I0 will be like starting from negative, that is minus I0. Okay. So let us start the circuit operation from T by 4. So from T by 4 to T by 2, it is like a S1, S2 are turned on. Okay, S1, S2 are turned on. Actually, strictly speaking, from 0 to T by 2, we are applying the controlling signal to the S1, S2. And from T by 2 to T, we are applying the controlling signal to S3 and S4. Okay, but actually S1, S2 are turning on at T by 4. And S3, S4 are turning on at 3 T by 4. Okay, so let us discuss from T by 4 to T by 2. For omega t is equal to T by 4 to T by 2. T by 4 to T by 2. Am I not audible? Audible, na? Yes, yes, yes. Okay, okay. For omega t is equal to T by 4 to T by 2, actually S1, S2 conducts, right? So when S1, S2 conducts, it is like S1 and S2 both are in a on state. So let me write here, S1 and S2 are in a on state. S1, S2 are in a on state. So when S1, S2 conducts, how the current will flow? Current flows from Vs, S1 load, S2 and again back to the Vs. Na? In this loop, the current flows. So you can check here, inductor go on storing the energy, right? Inductor is storing the energy. What are the I0, positive or negative? When S1, S2 conducts, current in the load branch is from left to right. So I0 will be positive only, right? So let me write here, inductor stores energy. Inductor stores energy. I0 is a positive. I0 is a positive only, right? So I0 positive. What about the V0? Can we apply KVL to the loop? Yes, it is a plus Vs minus V0 is equal to 0. No? Plus Vs minus V0 is 0. So therefore, V0 is equal to Vs. So here V0 is a Vs and I0 is increasing because inductor is storing the energy, right? So here you can check during T by 4 to T by 2, I0 is increasing, inductor is storing the energy, switches S1, S2 are in a conduction mode. Output voltage V0 is equal to Vs only, is equal to Vs only. Okay. So now it is like from T by 4 to T by 2, inductor has stored the energy. And at T by 2, at T is equal to T by 2, current flowing through the inductor is a positive. It is a non-zero current. The direction of the current, if current is positive, is direction of the current is from in the load branch, it is from left to right, right? So now at T is equal to T by 2, we are removing the controlling signal of the switches S1 and S2. So what will happen? S1, S2 will turn off. S1, S2 will turn off. Okay. And now we are applying the controlling signal to the switches S3 and S4. But whether our inductor will allow the switches S3, S4 to turn on immediately? No. Because at T is equal to T by 2, inductor current is a positive, it is a non-zero current. Okay. So after T by 2, first of all, inductor will release the energy. So how the inductor will release the energy? This inductor will release the energy through D3 in opposition to that of the Vs and D4. In this loop, the inductor releases energy. In this loop, the inductor releases energy. Yes or no? So after S1, S2, which two devices will be in a conduction mode? D3 and D4 will be in a conduction mode, right? So it is like current is flowing or the power flow is from load to the source. Okay, load is feeding back the power to the source. Okay, so here you can check inductor releases energy, so that's why current is decreasing. You can check when D3, D4 conducts, what is the direction of the current in the load? It is again from left to right, means the direction of current is positive only, but as inductor is releasing the energy, current is decreasing. Okay, so let me indicate here. Yes, for omega t is equal to T by 2 to 3 T by 4. It is like a D3 and D4 conducts. D3 and D4 conducts, right? D3, D4 conducts. Inductor releases energy. Inductor L releases energy. Releases energy, right? So when inductor releases energy, what is the I0 here? You can check the load current. It is from left to right only, na? So I0 is positive. What about the V0? Yes, we can check. simply apply KVL to this loop. Current is flowing like this now. So apply KVL to this loop. It is minus V0 minus Vs is equal to 0. Minus V0 minus Vs is 0 means V0 is minus Vs. V0 is equal to minus Vs. Okay. So load voltage is negative. Load current is positive, but it is decreasing. Okay. So we can check T by 2 to 3 T by 4. Load current is decreasing. Inductor releasing energy. And our load voltage is a negative here, right? What is the value of this voltage? It is a minus Vs, right? Minus Vs. Which two devices will be in a conduction mode? D3 and D4 will be in a conduction mode. Till 3 T by 4, it is like inductor has released the energy. Now at 3 T by 4, it is like S3 and S4 will turn on. Our devices S3 and S4 will turn on. So once S3, S4 turns on, current will flow like Vs, S3, load, S4, and again back to the Vs. In this loop, the current will flow. Yes or no? So if the current is flowing in this loop, so what about the load current? It is a positive or negative? You can check. Current in the load branch, it is from right to left. So I0 is negative. Okay. Inductor go on storing the energy now. Right? I0 negative. Inductor will store the energy. Okay. So let me write here for T is equal to 3T by 4 to T. S3, S4 conducts. S3, S4 conducts. Inductor L stores energy. Inductor L stores energy. Okay. I0 will be increasing, but it is a negative now. I0 is a negative. What about the V0? You can check. Simply apply KVL to this loop. When S3, S4 conducts, apply KVL. It is plus Vs plus V0 is equal to 0, right? Plus Vs plus V0 0 is equal to 0 means V0 is minus Vs. Okay. V0 is equal to minus Vs, right? So it is like inductor has stored the energy from 3T by 4 till T. Okay. You can check at T is equal to capital T. Here it should be T. At T is equal to capital T. What is the current here? This current is a negative and it is having a high value now, right? Non-zero value means current flows to the inductor at T is equal to capital T. The direction will be like, yes, from right to left, right to left. Now at T is equal to capital T, we are removing the controlling signals, okay, of S3 and S4. So our S3, S4 will turn off, right? So what will happen? This inductor will go on releasing the energy through D1 and D2 now. So how the inductor releases energy? Yes, it is like L, D1, Vs, D2, and again back to the L. In this loop, the inductor releases energy. Okay. So when inductor releases energy, what is the current in the load branch? It is flowing from right to left now, right? So therefore, I0 will be negative, right? So D1, D2 conducts, I0 is negative. Let me write for T is equal to T2. It is like a 5T by 4. Okay, 5T by 4. Or in the continuous cycle, it is like T is equal to 0 to T by 4. T is equal to 0 to T by 4. Both are same, right? Both are same. So here, which diodes are in a conduction mode? D1, D2. D1, D2 conducts. So it is D1 and D2. These two conducts. Inductor releases energy. Inductor releases energy. What about I0? I0 is negative. V0, you can check the V0, right? In this loop, apply KVL. It is like a plus V0 minus Vs is equal to 0. Plus V0 minus Vs is 0. Means what? V0 is equal to Vs. V0 is equal to Vs. Is this clear? Right? So you can check from T to 5T by 4. We'll be having V0 is Vs and I0 from T to 5T by 4. I0 is negative. Okay, it is decreasing. And from T to 5T by 4, whatever the waveform we're having, the same will repeat from 0 to T by 4 also, no? Right? So same here we're in. So again, in the single phase half bridge inverter also we discussed that if the load is purely inductive, the nature of the current is a triangular wave. Okay, it is a linearly increasing, linearly decreasing. Okay, so in the single phase full bridge inverter also with the L load, we are having the nature of the current is a triangular wave only. Okay, triangular wave. Next, you can check the V0 nature. V0 is a square wave, right? V0 we are having it is a square wave only, right? Now, can we write for T is equal to 0 to T by 2? Okay, for t is equal to 0 to t by 2. What is V0? V0 is equal to Vs. For t is equal to 0 to t by 2, we are having V0 is equal to Vs. Okay. Now what is V0? In the load we are having only inductor na. So V0 is equal to L into di0 by dt. So can I write it is a L into di0 by dt is equal to, it is a Vs, right? So therefore di0 by dt is equal to Vs by L. What it indicates? This is the slope. This is the slope, right? So this is the slope of I0. Slope of I0. Load current waveform. Slope of I0, right? Further, we can write it as di0 is equal to Vs upon L into dt. Na? Integrating both the sides, it is integration of di0 is equal to integration Vs by L dt. This can be written as I0 is equal to Vs by L into t, right? Therefore, I0 is equal to Vs by L is constant na, into time t. Okay, so you can check here your I0 is like a some constant into t na, right? So therefore, it is like y is equal to mx, right? So that's why here we are getting the I0 waveform. It is like a linear type shape. Okay, it is like a linear type shape, right? So I0. Now, can we find the I0 value or the peak value of the load current and the peak to peak ripple in the load current? Yes, we can find. So let me write di0 by dt again. di0 by dt is equal to, we wrote it is a Vs by L. Na? Same thing I have again written. di0 by dt is equal to Vs by L. Now you can check during 0 to t by 2 how the current I0 is changing. Current I0 is changing from minus I0 to the plus I0. So what is di0? Final value minus initial value, that is I0 minus of minus I0. So let me write it as I0 minus of minus I0 divided by how the time is changing. Time is changing from 0 to t by 2 na. So it is like t by 2 minus 0. So it is equal to Vs by L. Further, let me write it as 2 times I0 divided by t by 2 is equal to Vs by L. So from this I can write I0. Yes, therefore I0 is equal to, this can be written as Vs divided by L, okay, into t by 2 and divided by this t, means it will be like a 4. So this can be written as Vs into t by 4L. So I0 is equal to Vs into t divided by 4L. This is peak value of inductor current or load current. Peak inductor current. Peak inductor current, or you can say it is a load current. Load current, right? So this is the I0. Now can we find the peak to peak ripple in the load current? Yes. Peak to peak ripple in load current. Peak to peak ripple in load current. Load current is changing from minus I0 to plus I0. Na? So peak to peak ripple in the load current is nothing but 2 times I0. Yes or no? We check. Load current is changing from minus I0 to the plus I0. So peak to peak is like I0 minus of minus I0. So it is a 2 I0, right? So which is equal to 2 into Vs into t divided by 4L. So this can be written as Vs into t divided by 2L. Okay. This is the peak to peak ripple in the load current, right? Next, again, if you check the waveform, can we say that here each device or each switch conducts for t by 4 time only? You can check from 0 to t by 4, d1, d2 conducts. T by 4 to t by 2, S1, S2 conducts. Again, t by 2 to 3, t by 4, this time difference is t by 4 only. D3, D4 conducts, and so on, right? So here, yes, we can say that each device or each switch conducts for t by 4 time. Okay, t by 4 time, right? So each switch conducts for t by 4 time. Is this clear to all? Right? So this is about your pure inductive load. Pure inductive load. Okay. Further, we can find the expression of I0 also, but it is not required. Okay. In the half bridge inverter, we have discussed how to find the I0 expression. Okay. Here it is not required because yet they have not asked any question regarding your I0 expression specifically. Okay. Right. But they have asked a question sometimes like what is the slope of the I0? What is the peak value of the I0? Right. Peak to peak ripple in the load current. Right. And sometimes they ask the questions like generally they give the frequency of the inverter and they ask the questions like for how much time interval the diode will be in a conduction mode or how much time the diode conducts, okay, or each switch conducts. These type of questions they have asked. Okay, so let me write here. Nature of the voltage, output voltage is a square wave. Yes, nature of output voltage, that is V0. It is a square wave. And what is the nature of I0? It is a triangular wave. Triangular wave, right? So this is about the L load. Now let us discuss the RL load. Let us discuss the RL load. Yes. Single phase full bridge inverter with RL load. Yes, single phase full bridge inverter with RL load. Yes, same circuit diagram. Vs supply voltage, S1, S2, S3, S4, D1, D2, D3, D4. Load is RL. Voltage across load is V0. Current flowing through the load, it is a I0, right? So waveform. Yes, let me draw the waveform on this page. T by 2, T, 3T by 2, right? V0 waveform is a square wave only. Which harmonics are present in the output voltage of bridge inverter? Yes. Which harmonics are present in the output voltage of bridge inverter? Exponential rise, exponential fall. Again, it is a rise. Okay. And again, it is fall. Let me write here. It is a T1, T by 2, T2. This is a T, right? T3, and it is like a 3T by 2. Yes, which harmonics? Odd harmonics are present, right? Only odd harmonics. Even harmonics are absent. Correct. Okay. So which switches will be in a conduction mode? T1 to T by 2. It is like S1, S2. Okay. So it is S1, S2 conducts. After that, D3, D4, S3, okay, S1, S2, D3, D4, right? It is like again it stores the energy. Correct it. Should be like this. This it is a peak, right? And after that it will be like this. This is like a S3, S4, and again D1, D2. Okay, so yeah. Let us discuss the circuit operation. Yes. Single phase full bridge inverter with RL load now. Now here in the load we are having a resistor and the inductor. We know inductor is the element which stores energy and also it releases the energy as well, right? So here for at omega t is equal to at t is equal to small t1 to t by 2, S1 S2 starts conduction. Okay, so here S1 S2 turns on. So when S1 S2 conducts, current will flow from Vs S1 load S2 and again back to the Vs. In this loop the current will flow. Inductor will go on storing the energy. Current flowing through the load is a positive, right? And voltage across load is a Vs. So you can check here during this interval, V0 is equal to Vs, I0 is positive. Inductor go on storing the energy, right? Inductor stores energy. After that, what will happen after T by 2? Yes, it is like inductor, sorry, S1, S2 turns off and our inductor will release the energy through diodes D3 and D4. So it is inductor will release energy through D3, D4 in opposition to that of the supply voltage, in opposition to that of the supply voltage, right? So here when inductor releases energy, I0 is decreasing. I0 is positive only. You can check in this loop, the current in the load branch, it is from left to right. So I0 is positive only, but it is decreasing as inductor is releasing energy. Inductor releases energy. So here as inductor releases energy, your I0 is decreasing. Actually, this T2 should be at this side, right? Strictly speaking, this T2 should be at this side. Okay, so this T2 should not be at very close to the T, right? It should be here. Like this will be having. Okay, so let me yes, this is your D3, D4. Next, what will happen? This is like T2. So from T by 2 to T2, we are having the switches D3, D4 conducts. Next, at T is equal to T2, at T is equal to T2, D3, D4 turns off, and again next two switches, that is S3, S4 conducts. So current flows from Vs, S3 load, S4 and again back to the Vs. In this loop current flows. Okay, so if the current is flowing into this loop, you can check I0 is a negative, inductor go on storing the energy. Okay, okay, and again you can check what is the V0. If the current is flowing into this loop, V0 you can apply KVL, plus V0 plus Vs is equal to 0 now. Plus V0 plus Vs is 0, means what? V0 is minus Vs. So here V0 is a negative. You can check V0 is a negative here. Okay, and at the same time current is increasing. Current is increasing, right? So current increases means yes, inductor go on storing the energy. After this instant, again what will happen? Yes, our switches S3, S4 turns off, switches S3 and S4 turns off, and next two diodes will be in a conduction mode. So this is S3, S4. These two will be in a off state, and the diodes D1 and D2 starts conduction. So current is flowing like this. Current will flow like this. Okay, inductor will release the energy through diodes D1 and D2. So when current is flowing in this loop, that is in the anti-clockwise direction, I0 is a negative, right? Inductor releases energy means I0 should decrease. I0 will decrease. Inductor is releasing the energy. What about the V0? You can check. Positive terminal of the V0 will be connected to the positive of the Vs. Negative of the V0 will be connected through D2 to the negative of the Vs. Okay, so V0 is equal to Vs only, right? So V0 is equal to Vs. So you can check when D1, D2 conducts, load current is negative. Here voltage is positive, right? Voltage is a positive, right? So again, this should be at this side. While releasing the energy, it will be close. Whatever we indicated in the half bridge. Again, this slope depends on, yes, and this should be at this side. And here, let me indicate like this. Here it is like a D1, D2. So same D1, D2 here. Okay, so near to this 0, near to T/2, near to T, right? These instants will be there, right? So yes, yes. No, operation is not same as that of the L load. Yeah, operation is same, you can say, but the waveform nature is different because of the presence of resistor. Because of the presence of resistor. Okay, so yes. Next. Now, what is the V0 RMS here? V0 RMS is equal to Vs only. V0 RMS is equal to Vs na. You can check here, magnitude is Vs. Here it is minus Vs na. So V0 RMS is equal to Vs. If I want to find the I0 RMS, how to find the I0 RMS? We have discussed in the yesterday session. How to find the I0 RMS of this waveform? For that, we need to find the I1 RMS, I3 RMS, I5 RMS, yes or no? And we need to put it under root I1 RMS square plus I3 RMS square plus I5 RMS square plus I7 RMS square, etc. Yes or no? Right? Means we need to write the Fourier series expression. Okay. So here, let me write the Fourier series expression. Fourier series expression. What is the Fourier series expression of V0? Summation over n is equal to 1, 3, 5, 7 up to the infinity. Whether the V0 is same as that of the R load V0? Yes. In the R load also we had a V0. The waveform is similar to that of this thing. Okay. So in the R load we represented V0 is equal to, it is a 4 Vs divided by n pi into sine of n omega t na. Similarly, can I write I0 is equal to summation over n is equal to 1, 3, 5, 7 up to the infinity. It is a V0 divided by impedance. Okay, so it is a 4 Vs divided by n pi into Zn into sine of n omega t minus phi n. In this case, it is a RL load. So what about the Zn? Zn is equal to under root R square plus n omega L bracket square. Let me write. Yes, Zn, I'm writing here. Zn is equal to under root R square plus n omega L bracket square. And what about the phi n? Phi n is equal to tan inverse of n omega L divided by R. Na? The meaning is your output voltage consists of only odd harmonics. Fundamental component is definitely there, and the odd harmonics. Output current also consists of only fundamental components and the odd harmonics. Okay. Similarly, from this we can find the I01, right? After that we can find I03, I05, I07, etc. Okay. So how to find that I0 RMS? I0 RMS is equal to under root I01 RMS square plus I03 RMS square plus I05 RMS square plus so on. Yes or no? Right? So this is the expression of I0 RMS. Right? So next, what about the P01 output power at fundamental frequency? Output power at a fundamental frequency. At a fundamental frequency. So we can write P01 is equal to V01 RMS into I01 RMS into cos of phi 1. Similarly, we can write P03 is equal to V03 RMS into I03 RMS into cos of phi 3. Similarly, we can write for P05, right? Any value, any output power at any order of frequency you can write. Okay. And altogether we can find P0 is equal to P01 plus P03 plus P05 plus P07, etc. Right? So like this, we can find the output power. Right? So for RL load, we're having, yes, this expression. Okay, for I0. Next, for L load, for half bridge inverter, we have already written for L load. In the same way, we can write for purely inductive load also in the full bridge inverter. Okay. So next, now let us discuss if the load is RLC, then what will happen? If the load is RLC, then what will happen? Let us discuss. So if the load is RLC, then what will happen? Let us discuss. Single phase full bridge inverter with RLC load. Okay, now load is a RLC we are having, right? RLC means in the load now we are having a capacitor as well. Okay, we are having a capacitor as well. So now let us discuss. Before this, whatever we discussed for half bridge inverter as well as full bridge inverter, whether the output voltage changes according to the nature of the load? No. Yes or no? We already discussed. As in the voltage source inverter, your output voltage is a square wave only. It is independent of the nature of the load. It is independent of the nature of the load, right? So let me represent this thing. Okay, so as in voltage source inverter, V0, that is output voltage, is independent of nature of load. Independent of nature of load. So definitely in this case also we'll be getting output voltage is like this only. So let me write here T0 to T by 2, T by 2 to T, right? And like this. So we'll be getting this type of waveform. So it is like a T by 2 T. This value is Vs. This value is a minus Vs. Okay. So now what about the nature of the current? Let us discuss. Okay. So it is like this voltage is appearing across the RLC branch. Na? This V0 means what? Voltage across the load terminals. Voltage across the load terminals we are having. Okay. And across the load we are having a resistor, inductor and capacitor branch. Right. So can I represent equivalently? Can I represent equivalently the circuit like this? This is like a V0 we are having. Okay. And here we are having a resistor, inductor and capacitor. Please try to understand this. Means the meaning is this V0 means it is a square wave only. This V0 is nothing but a square wave. Okay, so this type of thing we are having. This is a V0. Means it is like a V0, that is square waveform. I am connecting across the RLC load. I am connecting across the RLC branch or the RLC load. means whatever the circuit we are having definitely is there, that is S1, S2, S3, S4, D1, D2, D3, D4. Obviously all these will be there only. Okay, but I have replaced that bridge circuit, okay, with this voltage source only, because we know at the end the output voltage of the inverter is voltage source inverter, it is a square wave only, na. Output voltage of voltage source inverter is a square wave only, right? So this is a V0 we are having, it is a square wave, right? This is a square wave we are having, that is the V0. Okay, so let me represent it as, this is your V0, right? It is a square wave. Now this square wave we are applying, right? It will be appearing across the RLC branch, right? Now let us discuss what will happen. Okay, let us discuss what will happen. Now here you can check, this magnitude is square wave, means V0 we are having this thing, na, we discussed 0 to t by 2, it is Vs only. Okay, so now you can check from t is equal to 0 to t by 2, t is equal to 0 to t by 2, what is V0? V0 is equal to Vs, and that voltage is appearing across RLC branch, na, right? So can I write, for t is equal to 0 to t by 2, for t is equal to 0 to t by 2, yes, what is the V0? V0 is equal to Vs, right? V0 is equal to Vs. Now the V0 is Vs, means between these 2 points it is like a voltage appearing is a Vs, okay, with a polarity plus here, minus here, and this voltage is like a Vs. Now are you getting the point? Okay, now can we apply KVL to this loop? Yes, it is like a plus Vs minus R into I0 minus L into di0 by dt minus 1 by c integration of I into dt is equal to 0 only, right? So further I can write Vs is equal to R into I0 plus L into di0 by dt plus 1 by c integration of I into dt, right? Okay, so now this is a Vs into Vs is equal to this term. Now can we take the Laplace transform? Yes, taking Laplace transform. Okay, so we can write it as Vs by S, right, is equal to R into I0 of S plus L into S into I0 of S plus, you can check 1 by c into integration, that is a 1 by cs into I0 of S. Okay, so definitely this should be the I0. Okay, so now we can write it as, which is equal to R plus Ls plus 1 by cs na, into I0 of S is equal to Vs by S, right? So further I can represent it as Vs by S is equal to, can I multiply with can I take the cross multiplication? Yes, it is a R plus Ls LCS square, R plus LCS square plus 1 divided by cs na, into I0 of S. So this can be written as, again taking the cross multiplication, RCS plus LCS square plus 1 divided by cs into I0 of S. Okay, this is like a Vs by S. So yes will get cancel out, right? So this can be written as, now I am taking LC out common, so it is like a Vs, therefore Vs is equal to, let me take the LC common, so it is like a LC into, in bracket it will be like a R by L into S na, so it is R by L into S, this is a R by L into S plus S square plus 1 by LC na, and again divided by this C as it is, okay, into I of S. So this can be written as, therefore Vs is equal to L into S square plus R by L into S plus 1 by LC into I of S. Now what this indicates, if you recall from the control system, this expression is nothing but the characteristic equation of the second order circuit na, RLC circuit is nothing but the second order differential equation, yes or no, right? So what it indicates? It indicates, yes, characteristic equation. Yes or no, right? So now from this, so here s square plus r by l into s plus 1 by lc is nothing but characteristic equation of RLC circuit. RLC circuit. Now from the control system, if you recall, generally we compare this characteristic equation with s square plus 2 zeta omega ns plus omega n square, na? Yes or no, right? So therefore let me show here. Yes, comparing this characteristic equation with s square plus 2 zeta omega ns plus omega n square. So from this you can check what is omega n. Therefore omega n is equal to 1 by root LC, na? Omega n square means 1 by LC. So omega n is 1 by root LC, right? So s square here it is also s square, no problem. Here it is a r by l, here it is a 2 zeta omega n, na? So can I write 2 zeta omega n is r by l, right? So let me write 2 zeta omega n is equal to r by l, is equal to r by l. So therefore I can write this can be written as zeta is equal to r by 2l into omega n. Further we can replace this omega n with 1 by root LC. So it is r upon 2l into 1 by root LC, 1 upon root LC. So you can check 1 root L cancel out. So it is like r by 2 into under root c by l, na? This is your zeta. This is the zeta. Zeta means what? It is a damping factor or a damping ratio, okay, or a damping coefficient, anything you can say. So this is your damping factor. Now the meaning is the nature of the current, okay, in the RLC circuit, it depends on your damping factor. We know in the damping factor we are having a 3 values. If one is greater than 1, second one is equal to 1, third one is less than 1, that is over damped, under damped and critically damped, right? So let me write here, if zeta is equal to 1, it is like a critically damped, critically damped. Zeta less than 1, it is a under damped. And zeta greater than 1, it is a over damped. Over damped. So if you check for these three values, how the system response or how response system response is nothing but your current nature, current waveform. How it will be I0. You can check. If the system is critically damped, if the system is critically damped, then what is the I0? That is the current in the circuit. It is a sluggish, na? Yes or no? So I0 will be like this. It goes to the peak and it takes very large time to settle. It takes a large time to settle. Okay, so this is for zeta equal to 1. If zeta is greater than 1, that is a, if it is a if it is over damped, then the nature will be like this. For over damped I am drawing, it will be like this. Okay. Next, it is also taking somewhat more time. And for under damped, if you recall from the control system, for under damped we are having, yes, fastest response, and it is having the some oscillations also. Okay, right? Damped oscillation, generally we say it, right? So this is for zeta equal to 1. Next one is for zeta greater than 1, and here it is zeta less than 1. This one is for zeta less than 1. Okay, so this type of, for different values of zeta, we are having the different current responses. We are having the different current responses. Okay, so now here you can check. Yes, if in the RLC circuit, if we select the value of RLC, if we select the value of RLC such that if the system becomes under damped, if the system becomes under damped. Okay, then which type of current response will be getting? Let us discuss here. Okay, so first thing is we are having the V0 waveform. Definitely it is a square wave. This is the time t 0 V0. This is your t by 2. This is t and this is a 3t by 2, right? This value is Vs and here it is a minus Vs. So what about the nature of I0? Let me first write it for xc greater than xl. Okay, that is zeta is less than 1. Okay, so the nature will be like this. So we'll be getting this type of nature actually. Okay, so this is the I0. This is for xc greater than xl, means current leads, because xc greater than xl I am saying. If xc is greater than xl, then it is like your zeta less than 1. Zeta less than 1. You can check zeta is equal to what we are having. Zeta is equal to r by 2 under root c by l, na? Right? So if xc is greater than xl, if xc is greater than xl means what? Xc is like 1 by omega c. If xc is greater than xl means your c is less than l. If c is less than l, this zeta will be less than 1. That is under damped. Okay. So for under damped circuit, okay, if RLC values are such that if zeta is less than 1, then we'll be getting this type of current in the circuit. Here you can check as xc is greater than xl, means capacitive reactance or the effect of capacitor is more than that of the inductor. So that's why the overall current, that is current which is flowing in the load, is leading to the voltage, load voltage by some angle. Okay, so it is like you can check, this will be starting like this, means at this side it will be having this type of waveform. So can I say that if I consider this angle is theta, if I consider this angle is theta, can I say that current is leading to voltage by angle theta? Yes or no, right? So next, similarly, we can draw the waveform for when xc less than xl, when xc less than xl. If xc is less than xl means what? Definitely I0 will be lagging, na? I0 will be lagging, right? So you can check the waveform will be like this. I0 time t. This is for yes xc less than xl. Okay, xc less than xl. So it is like a overdamped. Okay, zeta greater than 1 and it is a overdamped. Right? It will be like starting from this side here. Somewhat this type of response will be getting, right? So you can check current is lagging to voltage. Okay, current is lagging to voltage by some angle here. Okay, so this is the I0. This is the nature I0, right? So let me write here. If xc greater than xl, then I0 leads V0, and if xc less than xl, then that is xl is more, na? Then I0 lags, I0 lags V0, I0 lags V0. Okay, so now you can check here Now, out of these two, if you check here, if XC is greater than XL, then we are having the advantage. Which advantage we are having? Let us discuss. Okay, so suppose here at this instant current is becoming 0, and how the devices will be conducting, let me show here. It is like during this interval, okay, starting from here, so it is like S1 S2 conducts during this interval. It is like a D1 D2 conducts. Next, from this point to this point, S3 S4 conducts, and again D3 D4 conducts. Right, we will discuss why I have shown here D1 D2 after S1 S2, those things. Okay, so similarly here from this point to this point, okay, it is like a S1 S2. Next, from here to here, it is like a D3 D4. From this point to this point, let me show here, it is like a S3 S4, and again here to here, it is like a D1 D2 conducts. Okay, so now let us understand this. In the RLC circuit, if XC is greater than XL, can I say that the circuit behaves as a capacitive circuit? Please listen the question. In the RLC circuit, if XC is greater than XL, can I say that the circuit behaves as a RC circuit only? Because the effect of capacitive reactance is more than that of the inductive reactance. Na? So what is the overall impedance? We know Z is equal to R plus J into XL minus XC. Na? So if your XC is greater than XL, then Z is equal to what? It is like a R plus J into XL is lesser than that of XC. So the difference will be, yes, it is like a minus J into XL minus XC. Na? That is negative term will be there. Means the impedance, in the impedance, if we are having the negative term, then it indicates our circuit behaves as a RC circuit. Yes or no? Right? So if XC is greater than XL, the circuit will be behaving as a RC circuit. So it is like equivalent to, even though we are having a load is RLC, but as the XC is greater than XL, it is equivalent to the RC load only. It is equivalent to the RC load only. Right? So now let me show here. Yes, how the circuit operation will be. Okay, so for that, let me again redraw that circuit diagram. This is a R, L, and C. This is VS, S1, S2, S3, S4, D1, D2, D3, D4, RLC. Okay, so this is the V0, and here it is a I0. Now, yes, please try to understand here. If XC is greater than XL, if XC is greater than XL, means this circuit will behave as an RC circuit only. I am saying, if you check, for example, suppose in the load, we are having a resistance R is equal to 2 ohm. Suppose XL is equal to 3 ohm and XC is equal to 5 ohm. Okay, I am saying R is 2 ohm, XL is equal to 3 ohm, and XC is equal to 5 ohm. So what is the resultant impedance? R plus J into 3 minus 5. Na? So what is 3 minus 5? It is a minus 2, right? So can I say that it is like a 2 minus J2 ohm resultant impedance? So if resultant impedance is your 2 minus J2, the meaning is our current in the circuit, because current is nothing but what? Voltage divided by impedance. Na? So current in the circuit will be leading to the voltage across the circuit. That is the voltage across that load branch. Current in the load will be leading to the voltage across the load. Is this clear? This is very basic. If in a RLC circuit, if XC is greater than XL, circuit behaves as a RC circuit. In a RLC circuit, if XL is greater than XC, circuit behaves as a RL circuit. Yes or no? Right? So if XC is greater than XL, means capacitive effect will be more compared to that of your inductive effect. So that's why it is like a resultant, it will be like a RC circuit, and current in the circuit will be, that is current in the load will be leading to the voltage across the load by some angle. And here we have indicated that angle is theta. We have indicated that angle is theta. Now let us understand what is happening in the circuit. Okay. So it is like from this point, or let us I think from this point to this point, it is like S1, S2 are turned on. Okay, S1, S2 are turned on, right? So here you can check S1, S2 are in a conduction mode. Okay, S1, S2 are in a conduction mode. So it is like this. S1, S2 conducts. Current is flowing like this. Our capacitor go on charging. Okay. Now you can check at this instant what is happening. Current in the circuit becomes zero. At this instant, the current in the circuit becomes zero. So can I say that if the current in the circuit becomes zero, means it is like a current flowing through these two switches also becomes zero. So suppose instead of our controlled switches, fully controlled switches, suppose we have connected a thyristors here. For example, let us consider that we have connected a thyristors. Okay. So at this instant, the current has reached the zero value, because as the capacitor go on charging, definitely the current in the circuit will be decreasing. Na? So that's where current is decreasing here. Current is decreasing. At this instant, current becomes zero, right? Current becomes zero. Okay. So current is zero means it is like, suppose if S1, S2, S3, S4 are thyristors, then currents flowing through the thyristor reached the zero value. So it is like first condition for the commutation of thyristor has reached, right? Now, how that current becomes zero? That is due to the nature of the load. Yes or no, right? Whether we have done anything additional, or we have connected any additional element to decrease the current to zero? No, right? So here, please try to understand, current is reaching to zero here, right? So current flowing through thyristor becomes zero. And if you check the circuit operation, from 0 to T/2, actually we are applying the controlling signal to S1, S2, and from T/2 to T, we are applying the controlling signal to S3, S4. Na? So here from this point to this point, we are actually applying the controlling signal to S1, S2. And at this instant, we are interested in turning off S1, S2 and turning on S3, S4. But in the circuit, what is happening? Before this instant, only current flowing through the S1, S2 becomes zero. It is like, suppose S1, S2 are thyristors, then the current flowing through the thyristor will be reaching zero value at this instant. And after that, what will happen? Let us discuss. After that, what will happen? So suppose when S1, S2 are in a on state, capacitor will be getting charged. So how the capacitor will be getting charged? It is a plus here, minus here. Capacitor will be charged like this, na? Right? Once current reaches zero, it is like these two switches, S1, S2 will turn off. If those are the thyristors, definitely those will turn off. After that, what will happen? This capacitor will discharge, because we know when capacitor charges and capacitor discharges, what is the direction of current flowing through the capacitor? It will be opposite, na? So when capacitor charges, that is when S1, S2 are in on state, current flowing through the capacitor is like from left to right. But when S1, S2 turns off, that is when current becomes zero, means at this instant, current is reaching the zero value. So it is like our S1, S2 has turned off. And after that, this capacitor will discharge through D1, D2. Capacitor will discharge through D1, D2. So like this, the capacitor will discharge. Like this, the capacitor will discharge. Now you can check when the capacitor discharges like this. When the capacitor discharges like this, okay. So what about the I0? Definitely I0 will be negative now. So that's why here we are having the negative I0. We are having the negative I0, right? And you can check here. You can check here when capacitor discharges like this. What about the V0? V0 positive will be connected to the positive plate of the Vs. Negative terminal of the V0 will be connected to the negative plate of the Vs. So can I say that V0 is also Vs? So you can check after this instant D1, D2 conducts, means V0 positive, I0 negative. One more important thing, as I said, S1, S2, S3, S4 are thyristors. Here we are having the advantage of connecting the thyristor here, I am saying. Okay. How? Please concentrate here. First thing is, at this instant, current flowing through thyristor becomes zero, means the first condition for commutation has reached, right? After this, what is happening? The capacitor is discharging like this, na? But we know, in order to successfully commutate the thyristor or the SCR, we require to maintain the reverse voltage across the SCR. Yes or no? Right? So here, can I say that when the capacitor discharges through D1, D2, the on state voltage drop, think in a practical case, okay, the on state voltage drop across D1 and on state voltage drop across D2 will be appearing as a reverse voltage for S1, S2? Yes or no? When capacitor discharges like this, it is like D1, D2 will be in a conduction mode, and D1, D2 in a practical case, suppose these are the practical diodes, okay, then what will happen? Definitely these two diodes will cause some voltage drop, and the voltage across diode D1 will be like plus here, minus here, voltage across diode D2 will be like plus here, minus here. So whether this voltage across diode D1 will be appearing as a reverse voltage across S1? Yes. Similarly, voltage across diode D2 will be appearing as a reverse voltage across switch S2 na. So that's why our thyristor will successfully turn off. Okay. And can I indicate this point? Can I indicate this one means from this point to this point is nothing but the circuit turn off time for thyristor. Because how we calculate the circuit turn off time? It is the instant at which current flowing through thyristor becomes zero, and after that the reverse voltage is maintained, na? Right? So same thing here. Here after this, what is happening? Diode D1, D2 on state voltage is nothing but the reverse voltage, okay, for the respective thyristor. So that's why this is like a TC. In one of the examination, they ask the question related to this TC also. We are going to discuss that question, right? Yes. So please try to understand. If XC is greater than XL, if XC is greater than XL, then here if we use the thyristors, then we need not to go for the forced commutation technique. Okay, our thyristors can be turned off, okay, by naturally current becoming zero, and the reverse voltage will be maintained across the thyristor, and it is known as the load commutation. It is not a line commutation, it is a load commutation. It is like a load commutation. So let me write here, if or for XC greater than XL, right? Yes, if thyristors are used, thyristors means SCRs, okay, thyristors are used as switches, then thyristors will turn off due to load commutation, right? Already we discussed the load commutation in the chapter number 1, right? So same thing is happening here. RLC load, underdamped nature, XC greater than XL, current flowing through the circuit leads the voltage across the circuit by some angle. Okay, so therefore if current is leading the voltage, then definitely yes, here it is positive cycle of the V0 is like this. For I0 positive cycle is like this. For V0 negative cycle is here. For I0 negative cycle is here. So current is leading actually. So that's why this zero current, okay, will be before this instant na. So that's why the natural commutation is or we can say the load commutation is possible. We need not to go for the forced commutation here, but you can check here. In this case what will happen? Suppose XC is less than XL, that is XL is greater than XC. If XL is greater than XC, what will happen? It is like current is lagging the voltage. Current is lagging the voltage by some angle, na? Right? So let me consider this angle is theta. Let me consider this angle is theta. So current is lagging the voltage by angle theta here. Now important thing, yes, here we are actually from this point to this point, we are applying the controlling signal to S1, S2 at t is equal to 0 only. But our S1, S2 are turning on at which instant? At this instant. Means before this instant is like a inductor will be releasing the energy through the diode pair, na? Right? So you can check here. Now after this instant current is positive means what? S1, S2 are in a on state, right? Suppose S1, S2 are in a on state, right? So let me indicate in this circuit again. Suppose S1, S2 are in a on state. Now here XL is greater than XC, we are going to discuss. Okay, XL is greater than XC. So suppose S1 and S2 are in a on state. S1 is on, S2 is on. Current is flowing like this. Current is flowing like this. Okay, current is positive. So we are having this type of current waveform. Next, actually we expect that at this instant we are removing the controlling signals of the S1, S2 now, right? So at this instant, if we are interested in removing the controlling signal of S1, S2, corresponding to this instant, you can check, corresponding to this instant, you can check in the load, we are having the current is, this current is positive, yes or no? Current is positive means current flowing through the S1, S2 is a non-zero and it is a finite current, right? So suppose if I use the thyristors here, okay, and if I am interested to turn off the thyristors at this instant, is it possible to turn off the thyristor in a natural way? Not possible. We need to go for the forced commutation technique only, because corresponding to this instant, the current flowing through the thyristor is a peak value, that is the non-zero current, right? So at this instant, current is a non-zero. So in order to turn off the thyristor, I need to use the forced commutation technique only. But whereas if you compare the previous circuit, in the previous circuit, it was possible because current was reaching the zero value prior to this instant, right? So that's why the natural commutation, or you can say the load commutation, was possible. In this case, the load commutation is not possible. So if the thyristors are used, and if XC is less than XL, then we need to go for the forced commutation technique only, right? So let me write here. Yes, for XL greater than XC, XL greater than XC, right? Means current lags the voltage. If thyristors are used as switches, then thyristors will not turn off naturally, or you can say the load commutation. So therefore, in order to turn off the thyristors, we need to use the forced commutation technique. Okay, thus forced commutation technique is used, right? We need to go for the forced commutation technique. Is this clear? Right? Okay. So please try to understand, this question is important. This information is important because in one of the examination, they ask the straightforward question. For the single phase full bridge inverter RLC load, if XL is greater than XC, right? In order to turn off the thyristor, okay, we need to yes, and they will give the options like forced commutation, natural commutation, load commutation, etc. Okay, so please keep it in mind. If XC is greater than XL, definitely the load commutation, with the help of load commutation, yes, thyristors can be turned off. So we need not to go for the forced commutation, that is the additional commutation circuitry is not required. But whereas if XL is greater than XC, then forced commutation technique we need to use, right? So yes, here S1, S2 will be in the on state before this also. Okay, in the continuous cycle I have drawn this like this, right? In the continuous cycle it will be like this only. Okay, so yes, you can check RLC circuit, capacitor will be like you are getting charged, overcharged only. When XL is equal to X, one more student has asked a question, Mani Kumar. When XL is equal to XC, what will happen? Yes, if XC is equal to XL, what will happen? It is like a purely resistive circuit, na? If the purely resistive circuit, then V0 is your square wave, means I0 will be square wave only. Yes or no? Right? So please keep it in mind. Okay. So I think this you might have studied in your first year of the engineering. That is the basic electrical, right? RLC circuit. If XC is greater than XL, XC less than XL, XC is equal to XL, right? These are the three cases actually we're in. Okay. So we're having the nature like a sinusoidal waveform only. We're having the nature like a sinusoidal waveform, right? So more or less sinusoidal, near to the sinusoidal. Again, it depends on your value of X, that those things. what is the value of that resistor. Okay, it depends, because you can check in the commutation technique we discussed that load commutation, and in that case while analyzing the circuit we neglected the resistor, na load resistor. Then it is like we got the circuit like only LC circuit. For LC circuit, we are having the nature of the current is sinusoidal, na, right? So now some of the students are asking that, sir, how this negative cycle is possible? Negative cycle is possible because your voltage is here negative, na, right? So this whatever I analyzed here, this was for positive cycle. So similarly for negative cycle also, you can check for negative cycle also 0 to t/2 it is positive, na. But if t/2 to t, what will happen? Voltage is negative. So if voltage is negative, therefore what will happen? The negative current will circulate, right? Negative current is also circulating. Okay, so capacitor can only no capacitor. It is not like that. Capacitor is charging to the Vs only. You can recall your RLC circuit analysis. Capacitor is generally overcharged. Yes or no? Due to the inductor, na, that inductor stores energy and after that it releases energy again. So that when inductor releases energy, capacitor will be getting overcharged, right? Okay. So this is about the RLC circuit. So please keep it in mind, or let me summarize this. Yes. Single phase half bridge inverter or single phase full bridge inverter. If the load is a resistive, V0 I0 square wave, right? Second thing, if load is inductive, V0 square wave, I0 triangular wave. Third thing, if V0 is a if load is a RL load, V0 is a square wave only. And what about the I0? I0 is a exponential rise, exponential fall, right? So these are the three cases we discussed. Also, what about the RLC load and whatever the discussion we have made here? The same discussion, yes, will be applicable for your half bridge also. For the half bridge also, it will be applicable. Okay. So for RLC load, in that we are having the two cases. If XC is greater than XL, current will lead the voltage, and XC less than XL, current will lag the voltage, right? Current will lag the voltage. Okay. So, right. So now let us have some discussion on performance parameters of inverters. Theory bit. Okay. We'll discuss the performance parameters of the inverters, and after that we'll discuss the numericals. Okay. So strictly speaking, our inverter should give sinusoidal output, na? But whether our inverters are giving the sinusoidal output? No, right? So in order to judge the performance of the practical inverters, okay, we are having the three parameters. So in that, first one is harmonic factor of nth harmonic. Harmonic factor of nth harmonic. Nth harmonic. What it indicates? Harmonic factor of nth harmonic. Okay. It gives the information about contribution of nth harmonic. Contribution of nth harmonic in the output voltage of inverter. Okay. So harmonic factor of nth harmonic. Let me write. It gives information about contribution of nth harmonic in output voltage of inverter. In output voltage of inverter means how the harmonic is contributing to the output voltage of the inverter. Okay, that will be described by the harmonic factor of the nth harmonic, and it is given with the expression HFN. HFN is nothing but harmonic factor of the nth harmonic. Okay, which is equal to V0N RMS divided by V01 RMS. V01 RMS. Okay, V0N RMS means we know it is a output voltage at nth harmonic frequency and our output voltage at fundamental harmonic frequency. Okay, RMS value of output voltage at nth harmonic frequency, RMS value of output voltage at fundamental component. Okay, so or the fundamental frequency. Let me write here. V0n RMS is the RMS output voltage at nth harmonic frequency. Nth harmonic frequency. And V01 RMS is the RMS output voltage at fundamental frequency. Fundamental frequency. Is there any relation between the fundamental frequency and the output frequency of the inverter? Is there any relation between the fundamental frequency and the output frequency of the inverter? Suppose I have designed one inverter and that inverter is having the output frequency, output voltage frequency is 50 hertz. Then what will be its fundamental frequency? Come on. Yes, both are same, right? Both are same. How? You can check the Fourier series expression. Fundamental means n is equal to 1, na? And we are having the frequency like sine of n omega t. N is 1 means sine of omega t. Omega means 2 pi f, na? And what is that f? F is nothing but the output frequency of the inverter. Yes or no? Right? So always keep it in mind. The frequency of fundamental frequency is same as that of your output frequency of the inverter. Right? Output frequency of the inverter. Okay. So this is the harmonic factor of nth harmonic. Second one is the THD, total harmonic distortion. Second one is the total harmonic distortion. Yes. THD. Yes. What the THD tells about? Yes, it gives the information about, or it is a measure of closeness between the shape of the output voltage of inverter and the shape of output voltage at a fundamental frequency. Please try to understand. THD means what? It is, or it, yes, it measures closeness between shape of output voltage of inverter, okay, and output voltage at fundamental frequency. Fundamental frequency. The meaning is, yes, output voltage of the inverter wave shape, nothing but what? Actual output voltage, whatever the waveform we're having, na? We're having in a VSI, we're having a square wave, right? So it is this THD is nothing but what? Measurement of closeness between, yes, the wave shape of output voltage of inverter and the wave shape of the fundamental frequency or the fundamental component. That is V0 output voltage waveform and V01 output voltage waveform. Comparison between the two is nothing but your THD. What is the nature of V01? I am asking about the wave shape. What is the wave shape of the V01? Whether it will be triangular, whether it will be a square wave. Yes. Yes, it is a sinusoidal only. Yes or no? Pure sinusoidal. You can check. We are having the Fourier series expression. Right? Fundamental means it is n is equal to 1. And we are having some peak value into sine of omega t. Na? So it is a sinusoidal function. So always keep it in mind. Fourier series, what the Fourier series is doing? Fourier series is, yes, dividing your non-sinusoidal periodic waveform into the sinusoidal forms, na, of various frequencies, fundamental, second, third, fourth, fifth. Definitely In our inverter, the second, fourth, that is even harmonics are absent. Okay, so how it is given, represented like THD, or let me write percent THD is equal to under root, yes, V0 RMS square minus V01 RMS square divided by V01 RMS into 100, right? So it is under root V0 RMS square minus V01 RMS square divided by V01 RMS into 100, right? So you can check what the denominator indicates. The denominator indicates the total output voltage minus the fundamental. Total output voltage minus fundamental output voltage. The meaning is only harmonic output voltage is there, na? Right? So that's why it is a THD, total harmonic distortion. Okay, THD, right? So for an ideal inverter, if we want a sinusoidal output, na, definitely your THD should be 0. Definitely your THD should be 0. Means what? The fundamental share should be 100%, na? Right? So difference between these two should be 0. Okay, no harmonics at all. So this is the THD, total harmonic distortion. And third one is the distortion factor. Distortion factor, yes, of nth harmonic. Of nth harmonic. Yes, it is given with DFN is equal to V0N RMS divided by N square into V01 RMS. Okay, so yes, V0N RMS divided by N square into V01 RMS, right? So distortion factor of nth harmonic. So these are the three performance parameters of the inverters. Okay, so as long as your ideal inverter is considered, yes, what we require, harmonic factor of nth harmonic should be 0, na? Because if we are saying the ideal inverter means output should be sinusoidal. Okay, so harmonic should not be there. So that's why your HFN should be 0, no harmonics at all. THD also 0, right? What about the DF, distortion factor? No harmonics, so that's why V0N RMS will be 0. Okay, so now let us discuss numericals. Yes, after the numerical we will discuss the three-phase inverters. Okay, yeah, let us read this one. A single phase half bridge voltage source inverter has a resistive load of 2.4 ohm and input DC voltage is Vs 48 volt. Determine RMS output voltage at fundamental frequency, that is the V01 RMS, output power P0, total harmonic distortion THD, peak and average current flowing through switches and diodes, voltage rating of the switches. Okay, and repeat question 1 to 5 with single phase full bridge inverter. Okay, so now, yes, let us first note the data. Here we are having a single phase half bridge inverter. Let me write single phase half bridge inverter. Single phase half bridge inverter. Load is resistive. R is equal to 2.4 ohm. Vs, total voltage is given. It is a 48 volt. Right? It is not Vs by 2. It is a Vs they have given. RMS output voltage at fundamental frequency. Yes. How to find the RMS output voltage at fundamental frequency? That is V01 RMS. Yes, if you recall the Fourier series expression for single phase half bridge inverter. Yes, what we have written, V0 is equal to summation over N is equal to 1357 up to the infinity. It is a 2 Vs by N pi na, okay, into sine of N omega t. Okay, so for fundamental it will be like 2 Vs by pi, again divided by root 2 na, right? RMS means, so it is like root 2 into Vs divided by pi, root 2 into Vs by pi. Yes or no, right? So if you check, it is equal to, yes, root 2 into, now here it is Vs or Vs by 2. Yes, it's like root 2 by 5. 140, correct. So it is root 2 into 48 divided by 5. So it is like a root 2 divided by 5 into 48. 21.60, no? This is your V01 RMS. This expression was already written V01 RMS. What is the output power? What is output power? P0 is equal to V0 RMS into I0 RMS. Na? What is V0 RMS? It is a Vs by 2. What is I0 RMS? Vs by 2 R. Na? So Vs is 48 divided by 2 into 48 divided by 2 into, yes, R is 2.4. Yes, please check, it is 24 into 10, 240. No? This is your P0. Third bit, THD, total harmonic distortion. Just now we discussed that THD. Yes, under root V0 RMS square minus V01 RMS square divided by V01 RMS. If you want the percentage, then into 100. Okay, otherwise keep it as it is. So it is under root 24 square minus, it is 21.6 square divided by 21.6. Na? Yes, how much? .48, 0.43%. That is 0.4843. Right. Next, the peak and average current flowing through switches and diodes. Yes, fourth bit. Let us first find the peak current. Peak current through switches. Yes, what is the peak current flowing through the switches? Check the circuit operation. Half bridge inverter we are discussing. Peak current flowing through the switches. Check the switch current waveform. Yes. Vs by 2 R, na? Right? Switch current waveform we are having. It is a Vs by 2 R. Right? So it is equal to 48 divided by 2 into 2.4. So it is equal to 10 ampere. This is the peak current flowing through the switches. What is the average current through the switches? Average current through switches. Yes, how to find the average current? IS1 average, you can draw any waveform IS1. Okay, you can check for T is equal to 0 to T by 2. IS1 is a non-zero. It is a constant current, na? It is Vs by 2R. And from T by 2 to T, IS1 is 0, na? Right? So what is the average value? Vs by 2R divided by 2. Yes or no? You're getting the point. So it is equal to Vs by 4R. So which is equal to 5 ampere, no? Which is equal to 5. Right? Is this clear? Yes. What about the diodes? For purely resistive load, whether the diodes will be in a conduction mode? No, right? So peak and average current flowing through diodes is equal to 0 ampere. Okay, so peak current through diodes is equal to 0 ampere, and average current through diodes is equal to 0 ampere, right? So next, same repeat question 1 to 5 with single phase full bridge voltage source inverter. Okay, so this will be the homework for you. Same type of question they have asked, right? The only thing is you need to double the these values. Okay, so next, let us discuss next example. Okay, so a single phase voltage source inverter is feeding a purely inductive load as shown in the figure. The inverter is operated at 50 hertz in 180-degree square wave mode. 180-degree square wave means our square wave only. Assume that the load current does not have any DC component. Okay, that is load current is a no DC component means what? It is like whatever we have discussed now. Same, that is a triangular, same thing. The peak value of the inductor current I0 will be, peak value of inductor current I0 will be. They have asked the peak value, that is I0. We indicated na I0, small I0 waveform, it is changing from minus I0 to the plus I0. Yes or no? Right? So
hello, sir. In the previous question, you didn't discuss the fifth part, voltage rating of switches.
okay, voltage rating is remaining. Okay, fifth part. Yes. Sorry.
Sir.
Yes.
Sir, you have done for zeta greater than 1, that is for zeta is equals to 1 and zeta greater than 1. That is waveform actually you done slight mistake, I think, means exchanged, means the zeta value.
Exchanged means?
Means for the zeta greater than 1, you did zeta is equals to 1 and
okay, means in that I0 altogether whatever three waveforms are
over damped, it will take more time.
Critically it will take more time. Over damped also it will take more time. And under damped will take lesser time.
Under damped lesser time, then zeta is equals to 1, then zeta greater than 1.
Zeta equal to 1 will take very high time. It is a sluggish response.
Sir, actually it is actually
yes.
Okay, I will see.
Right?
Actually, this is a previous gate question.
So next, voltage rating of the switches. Yes, last bit. Yes, remaining fifth bit. Let me write. Voltage rating of switches. What about the voltage rating? We discussed this point in the yesterday session. Come on, what is the voltage rating of the switches? It is a VS, na? Yes or no? You can check the circuit diagram. How many times we're having the half bridge inverter? Right, so purely resistive load, this type of thing we're having. Okay, so yes, so this is S1, S2, D1, D2 na. How to find the voltage rating? This is Vs by 2, this is also Vs by 2. Yes, at a time only one switch will be in a conduction mode. So suppose S1 conducts, at that time S2 open na. So when S1 conducts across S2, how much voltage is appearing? Consider this voltage is Vs2. So how much voltage this S2 is required to be blocked? Yes, it is equal to Vs na. same voltage, whatever the potential here, same will appear here. It is acting as a short circuit, same potential here. Whatever the potential here, the same will appear here, same here, same here. Means whatever this full voltage is there, this full voltage will appear across the switch. Na? So what is the voltage rating of the switches? It is equal to Vs by 2 plus Vs by 2. That is the Vs only, right? So voltage rating of switches is equal to Vs is equal to 48 volt. Is this clear? Yesterday also we discussed this thing, right? Okay. Next, single phase voltage source inverter is feeding. Single phase voltage source inverter is feeding a purely inductive load as shown in the figure, right? The inverter is operated at 50 hertz in 180 degree square wave mode. Assume that the load current does not have any DC component. The peak value of inductor current I0 will be. Our task is to find the capital I0 value. Okay. They have given the 4 options, and after that, yes, what is the time duration of conduction of each diode in a cycle? Okay, so it is a purely inductive load. What will be the time duration of conduction of each diode? We discussed each diode or each switch conducts for T/4 time, na? Yes or no? Right? So let us discuss first this question, that is question number 1, and after that we'll focus on the second question. Okay, so let me write here. First question, yes. It is a 1 degree square wave mode. Frequency is given 50 hertz. If frequency is 50 hertz, that is nothing but your T is equal to 1 by 50, na? So it is equal to 0.02 second, na? Right? It is equal to 0.02 second. Okay. So now that is 20 millisecond. Okay. So now our task is to find the capital I0. So if you check here, the I0 waveform, whatever we discussed, wherein the I0 waveform, it is like this. Time T 0. Either you can memorize those expressions, whatever we derived, or okay, if you don't want to memorize, simply do the network analysis. Please listen how to do that network analysis. T/4, T/2, 3T/4, and here it is a T. Okay, so how is the current we are having? Current nature is like this. Current waveform. Yes or no? For purely inductive load, they have asked the peak value, na? That is nothing but this plus I0. They have asked. They have asked this plus I0 value, right? So you can check here. Corresponding to this point to this point. Okay, so from T/4 to T/2. Which two switches will be in a conduction mode? If you recall the circuit operation, from T/4 to T/2, we are having switches S1, S2 in on state, na? So when S1, S2 conducts, it is like S1 is on, S2 is on. Current is flowing like voltage, that is supply, S1 load, S2, and again back to the supply, na? In this loop, the current will flow, right? So simply apply KVL to this loop during T/4 to T/2. Are you getting the point? Okay, so let me write here. Apply KVL to loop during T is equal to T/4 to T/2. Yes, what is the KVL equation? Plus 200 minus switch S1 is on, na? Minus L into di0 by dt, right? So it is like L is nothing but 0.1. So it is a 0.1 into di0 by dt is equal to, you can check, this is short circuit and we are having only is equal to 0. So here, can I write it as 200 is equal to 0.1 into di0 by dt? So it is like 2000 is equal to di0 by dt, na? I have taken this 0.1 this side, left side. So di0 means what? Change in the current I0. How the current I0 is changing from T/4 to T/2? It is changing from 0 to plus I0. So what is the change? Plus I0 minus 0. So that is a plus I0. Divided by how? Yes, time is changing. dt means change in the time. T/2 minus T/4. Okay, so it is like a T/2 minus T/4. Okay, so let me write it as 2000 is equal to I0 upon T/4. Okay, so this can be written as we can write it as a 2000 into T is equal to 4 into I0. So what is T? we have written it is a 0.02. So you can check here, 2000 into 0.02 is equal to 4 into I0. So therefore I0, yes, how much? 10 ampere, right? 10 ampere. Is this clear? Okay. So if you check the options, correct option is option B. Next, second thing is the time duration of conduction of each diode, okay, in a cycle. Each duration of conduction of each diode means, you can recall how the switches are in a conduction mode here. S1, S2, D3, D4, S3, S4, and again here D1, D2, right? We know it is a T/4 now. Okay, so therefore conduction time of, second bit, conduction duration of each diode is equal to T/4. It is equal to 0.02 divided by 4. No? So it is equal to, I think, 5 milliseconds, right? 5 milliseconds. Check the options. Option A is the correct option, right? So this is a 5 milliseconds, correct? Okay. Okay, okay. Yes, first question, fifth part, anonymous attendee. Okay. So voltage rating of the switches they have asked. If you recall the purely resistive load, at a time one switch will be in a conduction mode, circuit operation. So when S1 is in a conduction mode, S2 will be in a off state, na? So how much voltage this S2 is required to block? It is like whatever the voltage that is appearing across it. So voltage across this is nothing but voltage at this point is voltage at this point, and simply apply KVL to this loop. Apply KVL to this loop, you will get answer. Plus Vs by 2 plus Vs by 2 minus Vs2 is equal to 0. So Vs is equal to Vs2, right? Okay. Okay. So next, yes, this one is bit interesting. A single phase bridge inverter shown in figure has an ideal transformer with primary turns equal to 10. N1 is given 10 for obtaining a fundamental frequency output voltage of 240 volt. Fundamental frequency output voltage they have told. Okay, that is a V01 RMS is a 240 volt. The number of secondary turns in transformer should be equal to, and they have given take pi is equal to 3. So if they are saying take pi is equal to 3, then you should take pi is equal to 3 only. Don't think like there is a printing mistake or those things. No, if they are saying pi is equal to 3, then for solving this numerical, we need to consider pi is equal to 3 only, right? So actual value of pi is 3.14, but as they are saying take pi is equal to 3, so therefore we need to take pi is equal to 3. If you take pi is equal to 3.14, then you will not be you will be getting the answer, but that answer, yes, will not be here in these options. Okay, so yes, the first thing, please try to understand the circuit. This is we are having a single phase full bridge inverter circuit, right? Input voltage is 12 volt. At the output side, that is in the load, what they have connected? They have connected a transformer. Okay, in the load they have connected a transformer, right? And number of turns of the primary it is given, that is a 10. Our task is to find the number of secondary turns, means our task is to find the N2. It is given that, yes, for obtaining the fundamental frequency output voltage, means at this side transformer secondary side, fundamental frequency output voltage is equal to 240 volt. They have given. Okay, our task is to find the N2. So let us first note the data. Yes, N1 is given It is a 10. Yes, transformer secondary side fundamental frequency output voltage. So let me write fundamental frequency output voltage at secondary side of transformer. At secondary of transformer means secondary side. Okay, let me indicate it as VS1. Okay, I'm writing it as a VS1, right? So VS1 is equal to 240 volt. Actually, this should be the RMS only. Now, by default, whatever the value they have given, it is RMS only, 240 volt. Okay, so fundamental frequency output voltage at secondary side of the transformer is VS1 RMS is 240 volt. It is given. N1 they have given. Our task is to find N2. Our task is to find N2. Right? Now, please try to understand here. N1 given, N2 we need to find. Secondary side fundamental frequency output voltage they have given, that is a 240 volt. Can we find fundamental frequency output voltage at the primary side? You can check us transformer circuit operation. You can check. This is the voltage source inverter. In the voltage source inverter, what will the output voltage waveform? It is independent of the load, nature of the load. So what is the output voltage waveform? It is a square wave. Yes or no? So how will this? Let me indicate this as a V0. Let me indicate this voltage as a V0 here. Okay. So how is the nature of this V0? We have already discussed the V0 is a square wave. 0. This is the V0 we are having. It is a square wave, na? 180 degree square wave mode, right? So this is like a T by 2. This is like a T. And what is this value? It is a full bridge inverter. So this magnitude should be equal to Vs, that is equal to 12 volt. Let me write it as a 12 volt. 12 volt. Now, for this waveform of V0, whether we are having the expression for V01 RMS, yes or no? We are having the expression na V01 RMS. Yes, let me write here. Yes, Fourier series expression of V0 of output voltage at the primary side. I am saying that is the output voltage of your inverter actually. V0. Yes, what is V0 is equal to summation over N is equal to 1357 up to the infinity. It is a 4 Vs by N pi na into sine of N omega t. Same expression we discussed earlier. So what is V01 RMS? That is a V01 peak divided by root 2. What is a V01 peak? V01 peak is 4 Vs by pi. Peak divided by root 2, that is a 4 Vs by pi divided by root 2 means what? 2 root 2 into Vs divided by pi. Yes or no? Right? 2 root 2 Vs divided by pi. So if you check, it is equal to 2 root 2 into Vs is how much? Supply voltage. It is a 12 volt. Na? So can I write it as into 12 divided by pi means here we need to take pi is equal to 3 only. Right? So it should be 3. So if you check, this value is equal to 24 by 3. Na? That is 8 root 2. Okay, let me write it as 8 root 2 volt. Okay, or you can find it in a fraction also, doesn't matter. Okay, so 8 root 2 volt we are having. This is the V01 RMS at the primary side. So primary side fundamental frequency voltage is 8 root 2 V. Secondary side fundamental frequency voltage is 240 volt. Now we know in the case of transformer, secondary side voltage divided by primary side voltage is equal to N2 by N1, right? So can we write? So yes, in a transformer, can we write, this is transformer. Okay, so can we write V01 RMS divided by VS1 RMS. VS1 RMS is equal to N1 by N2. Yes or no? Right? So check what is V01 RMS. It is a 8 root 2 divided by VS1 RMS. It is a 240, which is equal to N1 by N2. N1 is a 10, na? Divided by N2 we need to find. So from this, can we find N2? N2 is equal to 240 into 10 divided by 8 root 2. right? Okay. Yes. How much? (300 by root 2 na? Which is equal to your 150 root 2 na, right? This is the N2. Correct? Is this clear? Yes. So please try to understand. Very simple question actually, but at the first time, if we see this type of diagram, means in the load, it is like a transformer, what they have connected. Okay, we feels somewhat difficult, but it is not like that. Always keep it in mind. In the bridge inverter, output voltage is independent of type of the load, right? Okay. So next, let us discuss this question. Single phase voltage source inverter is controlled in a single pulse width modulated mode. Okay. We will discuss it later on because it is related to your single pulse width modulation. Yet we are not discussed about the pulse width modulation technique, right? We'll discuss it later on. Yes. Let us discuss this question. A single phase full bridge voltage source inverter delivers power to RLC load with R is equal to 3 ohm, XL is equal to 12 ohm. The bridge operates with a periodicity of 0.2 millisecond. Calculate the value of C so that load commutation is achieved, right? So that calculate the value of capacitor C so that the load commutation is achieved. TQ for SCR is 12 microsecond. Device turn off time they have given. It is a 12 microsecond and factor of safety is 2. Factor of safety is 2. Assume load current consists of only fundamental component. Okay, so fundamental means only sinusoidal waveform we're having. Okay, that we need to assume. So now this question is related to your RLC load. Okay, and our task is to find the value of capacitor so that load commutation is achieved. Okay, load commutation is achieved, right? So now let us understand it. First thing is single phase full bridge inverter. We are having R is given. It is a 3 ohm. XL is equal to 12 ohm. The bridge operates with a periodicity, means T, capital T is equal to 0.2 millisecond. That is 0.2 into 10 to the power minus 3 second. So therefore frequency is equal to 1 by T na. So it is equal to 1 by 0.2 na into 10 to the power minus 3. So if you check, it is equal to yes 5,000 na, 5,000 hertz. This is a frequency. Next, calculate the value of C. We need to find TQ. They have given it is a 12 into 10 to the power minus 6 second. Understand the what is the meaning of factor of safety. So first of all, let me write factor of safety is equal to 2. Our task is to find the C, right? So what the factor of safety indicates? Yes, the device turn off time is a TQ, that is a 12 microsecond. Means device requires a minimum 12 microsecond. Device requires a 12 microsecond to turn off. Factor of safety is nothing but this factor indicates for how much time we need to maintain the reverse voltage across the device. Okay, generally factor of safety, let me write here. Let me write the factor of safety is equal to circuit turn off time divided by device turn off time. Device turn off time means if device is requiring 12 microsecond to turn off, then we need to provide factor of safety 2 means what? We need to provide the circuit turn off time. That is, we need to maintain the reverse voltage across the device for minimum of 2 into 12 microsecond. That is nothing but 24 microsecond. Are you getting the point? Okay. So here, see, factor of safety is 2, which is equal to circuit turn off time, that is TC, divided by device turn off time is TQ. Na? It is a 12 into 10 to the power minus 6. So therefore TC is 24 into 10 to the power minus 6 second. Now, are you getting the point? In the I0 waveform, we have indicated TC also. Na? If you check whatever we discussed here, yes. Yes. Yes, here we have indicated this TC also. So this TC just now we have calculated. It is a 24 microsecond. Yes or no? So TC is 24 microsecond, right? So corresponding to that TC, can we find the angle? Right? Because we know from this point to this point means it is like a one complete cycle. Na? So that is like a 360 degree. So it is like a 360 degree. We know T. So for 360 degree, we are having the T. So corresponding to TC, can we find the angle? Yes, we can find the angle. Okay, so let me write here. Yes. So TC we have calculated. Now, what is the omega TC? Omega TC, or let me write angle corresponding to time. Angle corresponding to time TC. Okay, angle corresponding to time TC, that we need to find. Okay, we know for T it is a 360 degree. Na? Then for TC, let me write it as a X. T is nothing but one period complete. Na? That is a 360 degree. So TC is equal to, we need to find. Okay, for TC. So therefore I'm writing, therefore X is equal to 360 degree into TC. 360 degree into TC divided by T divided by T. So which is equal to 360 degree into TC is 24 into 10 to the power minus 6 divided by T is, we know T is equal to 0.2 into 10 to the power minus 3. So it is equal to 24 divided by 0.2. Into 360. Yes, it is a 43.2 na degree. What it indicates? Yes, it indicates the angle corresponding to the TC. The meaning is our current which is flowing through the circuit should lead the voltage by this much angle. Are you getting the point? Then and only then our SCR will successfully turn off. Are you getting the point? Right? Means this is nothing but angle corresponding to TC. Angle corresponding to TC. Right? So angle corresponding to TC. TC. So now for load commutation, okay, I0 should lead V0. I0 should lead V0 by how much angle? 43.2 degree, by 43.2 degree, right? So for load commutation, I0 should lead the V0 by angle 43.2 degree, right? Then and only then the load commutation is possible, na? Right? They have given, because factor of safety also they have given, means we need to maintain the reverse voltage for minimum of 24 into 10 to the power minus 6 seconds, right? So corresponding, we have calculated the angle. Okay, we have calculated the angle. Now, if the angle between V0 and I0 is 43.2 degree, so now can I write? Yes, we know the angle between V0 and I0, angle between V0 and I0, okay, is nothing but what? It is a tan, it is nothing but what? Theta, na? Or you can write theta or phi also, doesn't matter, which is equal to tan inverse of, we are having the RLC load, na? So can I write it as omega L minus 1 by omega C divided by R. They have given that load current consists of only fundamental frequency. So that's why I'm writing it as only theta, or let me write it as theta 1 also. And it is instead of n, it is a 1 only, na, n is 1. So it is omega L minus 1 by omega c divided by r. Okay. So that is XL minus XC you can write. Okay. So which is equal to tan inverse of XL minus XC divided by r. Tan inverse of XL minus XC divided by r. Now, our this theta 1 is a leading or lagging? Theta 1 is leading, na? So that's why here we need to consider the angle is negative. We need to consider the angle is negative, right? Because you can check in the REL branch, right? We have considered in the REL load, we have considered the phi n is equal to tan inverse of omega L by r, na? Now in this case, if your current is required to be lead the V0, na, then your 1 by omega c should be greater than omega L, right? So that's why this angle should be means tan inverse of this negative term, means that's why here it is a negative we need to consider. Okay, so let me write it as a, which is equal to 43.2, right? Minus of 43.2 degree. I'm writing minus. So therefore, let me write it as a minus of 43.2 degree is equal to tan inverse of XL minus XC divided by, sorry, XL they have given. How much XL they have given? It is a 12, no? So it is a 12 minus XC is, we need to calculate, divided by R. R is 3, right? So therefore, tan of 43.2 or minus is equal to 12 minus XC divided by 3. So if you check, minus 0.939, okay, is equal to 12 minus XC divided by 3, right? So therefore we can write XC is equal to, XC is equal to, yes, from this please find XC, please find XC here. Yes, how much XC? $14.8171, right? 14.8171. 14.8171 ohm, na? That is the capacitive reactance. And what is the XC? XC is equal to 1 by omega c, as XC is equal to 1 by omega c. Okay, so therefore we can write 14.8171 is equal to 1 by omega is 2 pi f into c. So therefore c is equal to, let me write c is equal to directly here. Therefore c is equal to 1 upon 2 pi f into this thing, 14.8171. Okay, so you can check f, we know it is a 5000, na? We have written here frequency f is equal to 5000 hertz. Okay, so take it as 5000. So it is 1 upon 2 pi into 5000 into 14.8171. Okay, please check how much. .15 microfarad, right? 2.15 microfarad. Are you getting the point? So please try to understand this thing. We need to consider here theta negative because current is leading, na? Right? So that's why if you check, if you write here theta is positive, you will get your XC as a negative. If XC is negative, their capacitor will be negative. Whether the capacitor value can be negative? No. right? So please keep it in mind. Yes, here as XC is greater than XL, na, then and only then the capacitor, then and only then the current can lead. So that's why the numerator will be negative. So that's why here we need to consider the angle should be negative. Okay, right? So yes. Next. Right. Last example we'll discuss, and after that we'll take a break. Right. Okay, so the above circuit shown in figure 1 is an inverter circuit with a DC source voltage of Vs, input voltage. The semiconductor switches are operated in such a manner that the pole voltages V10, okay, V10 and V20 are shown in the figure 2. Okay, in figure 2 they have given V10 and V20. Find the RMS value of the pole to pole voltage V12. Okay, V12, right? They have used here a word like a pole voltage, right? And the voltage V12. V12 is like voltage between these 2 points. V1 minus V2 is nothing but your V12. V12 is nothing but V1 minus V2. That is a straightforward. But let us understand what is the V10 and what is the V20. That is a pole voltage. Actually, in a practical case, what we are doing, we are generally connecting a capacitor, right? Let me indicate here. Let me redraw this net circuit. In order to provide the constant DC voltage, right? Let me indicate as a switch here. Instead of drawing these BJTs. Okay, so this voltage is Vs. This is like a C. This voltage is like a Vs by 2, and this is like a Vs by 2. And we are indicating it as a yes point O. This is like a 0.1, 0.2, and a 0.0. Okay. So generally in practical case, in order to provide the constant DC voltage to the inverter, where yes, connecting a capacitor here across the supply, because the thing is the voltage input to the inverter, right? This voltage we are giving to the inverter is nothing but like your output of the chopper circuit. Yes or no, right? And the chopper circuit, suppose in the worst case, suppose if the chopper circuit voltage is changed, okay, due to some reason, then it will affect on the performance of the inverter. So for that, in order to avoid this, generally we are connecting a capacitor here like this. So if the capacitors are connected like this, it is like this total voltage will be like Vs by 2 and Vs by 2 will be divided here. Okay, definitely this voltage is Vs only, but here we are getting Vs by 2, here it is Vs by 2. Okay, and the pole voltage is nothing but V10. This V10 is nothing but pole voltage. V20, that is potential difference between this terminal and this terminal, is nothing but your V20. These voltages they have given here. Now our task is to find the RMS value of the pole to pole voltage, that is a V12. Okay, so simply V12 means what? V10 minus V20. That's it. We're having V10 voltage waveform, we're having V20 voltage waveform. So from this, can we draw V12 waveform? Yes, you can check. Please be careful. This is theta axis, and the theta 0 means this point. Theta 0 means this point. It is not like this point. Please be careful. Theta 0 is nothing but this point they have indicated. Right? Means actually our waveform is starting. Theta is 0 means from this point we need to consider the waveform. Okay. So this is V10, V20 we are having. Theta 0 here means here it is also theta equal to 0. So now you can check V10 is here, V20 is here. This angle is phi, they have indicated. So omega for theta is equal to 0 to phi. Phi is nothing but this point now. So for theta is equal to 0 to phi, you can check V10 is plus Vs, V20 is 0 na. So what is V10 minus V20? V10 minus V20 is equal to Vs only, right? Next, from phi till pi, this is pi. Okay, so this is a pi here. So from phi till pi, V20 is Vs, V10 is also Vs. So what is the difference between these two? Difference between the two is equal to 0 now. From pi till this instant is nothing but pi plus phi. Pi plus phi. Your V20 is like a shifted, okay, by angle phi, okay. So pi to pi plus phi, you can check V10 0, V20 is Vs. So V10 minus V20 difference is 0 minus Vs, so that is a minus Vs. Similarly, we can check for 2 pi to 2 pi plus phi, because this is still 2 pi na, so it is like a one complete cycle. Okay, so let me draw the waveform of V12 first, and after that we will find the RMS value of the V12, RMS value of V12. Okay, so yes, so V12 waveform, let me draw. This is theta, theta is 0. Next we are having the interval like theta is equal to phi. Next we are having a pi. Next here it is a pi plus phi. And after that is 0, 5, pi, pi plus phi. And after that we are having directly 2 pi, right? So it is like directly 2 pi. So how is the waveform for V12? 0 to 5, Vs minus 0. So it is a Vs only. So 0 to 5, this is a phi, not, yes, this is a phi. So 0 to 5, V12 is a Vs. Is this clear? This is a Vs. Phi to pi, from phi till pi, both are Vs. So difference will be 0. So difference will be 0. Pi to pi plus phi, from pi to pi plus phi, this is 0, this is positive. So difference is minus Vs. Difference is like this, it is a minus Vs, right? So this magnitude is a minus Vs. And from pi plus phi to 2 pi, here it is pi plus phi, and till 2 pi you can check, this is 0, this is 0. So 0 minus 0 is a 0. So we'll be having the waveform like this. So this is like one complete cycle. Now our task is to find the RMS value of this V12 RMS. V12 RMS. How to find the RMS value? It is like 1 by 2 pi. Yes, let me write. Integration from 0 to 5 Vs square na into d theta. This is theta, so I am writing it as d theta, plus integration from pi to pi plus phi. It is a minus Vs square into d theta, right, to the power 1 by 2, right? So we can simplify it. It is like Vs square, we can take outside, Vs upon root 2 pi into this root, this 2 pi I am taken outside, Vs square I have taken outside. So into, in the bracket it will be like a 5 plus 5 to the power 1 by 2. So it is like a, yes, 2 will get cancelled now. So under root 5 by pi into Vs, right? Under root 5 by pi into Vs. Is this clear? No, here V12 means V1 minus V2. VAB is VA minus VB na? Yes. Is this clear? Under root 5 by pi into Vs. Okay, so right. So we'll take a break here, and after the break we'll discuss the three-phase inverters, right? Okay. We're going to do the detailed analysis of three-phase inverter, starting from the circuit operation. It's for drawing the waveforms, phase voltage, line voltage, your pole to zero voltage, right? And after that, Fourier series analysis of those waveforms also. Okay, so we start at, it's 7:22. We'll start at 7:40, right? Okay. Okay. So now we are going to discuss the capacitor I added in the previous example, right? Generally, the pole voltage, right, is nothing but the V10 or V20. These are the pole voltages, right? So in order to understand that pole voltage, I have represented it with two capacitors connected in series, and that is connected across the supply voltage. Generally, in practical case, we connect the capacitor. Why? Because we know a capacitor is the element which opposes the change in the voltage, right? And generally, for the inverter, the input voltage is nothing but the output of your chopper circuit, right? And if you check here, if due to some reason, in the worst case, if the output voltage of the chopper is changing, okay, by due to some fault or due to some reason, suppose the output voltage of the chopper has changed, then our capacitor will oppose that change, so that the inverter input will be maintained constant, right? So next, let us discuss a three-phase bridge inverter. Three-phase bridge inverter. So let us first draw the circuit diagram. In the three-phase bridge inverter, there are two modes. One is the 180-degree conduction mode and 120-degree conduction mode. The circuit diagram for both the modes, okay, is the same only, right? So we are having a input DC voltage. As I said, generally it is connected, yes, two series capacitors. Here we are using total 6 switches. S1, S3, S5, S4, S6, and S2. D1, D3, D5, D4, D6, and D2, right? The load is a three-phase load. Consider the load is star connected, right? Load may be star or delta connected, but let us consider here it as a star connected. Okay, so R, R, and R. Now load is star connected. This is the neutral point of the star. The load phases are like this is the phase A. Let me write this as a phase B of the load. This is a phase C of the load. Okay, A, B, C. These are the load terminals, neutral point. right? So definitely the voltage across A and N is nothing but your VAN, phase voltage of the load, phase A voltage. VBN is nothing but the phase B voltage. VCN is nothing but the phase C voltage. VAB is nothing but the line voltage. VBC line voltage. VCA line voltage, right? We know in a star connection, phase voltage and line voltage are not same. Yes or no, right? Line voltage is generally √3 into phase voltage. Okay, next. So please try to understand this connection. Wherever the supply voltage VS, we are using the 6 controlled switches S1, S3, S5, S4, S6, S2. Across each switch, a diode is connected D1, D3, D5, D4, D6, D2. Yes, for purely resistive load, there will be no functioning of a diode. Okay, so next I have shown the two capacitors connected in series across the voltage source VS. Yes, so this is like a point O. Okay, here it is a phase A, B, C, or this phase A can be represented here also, point A. This is like a phase B and this is like a point C, phase C. Okay, so VAO is nothing but your pole voltage. VBO, it is also pole voltage. VCO, it is also pole voltage. Okay, VAN, this is the phase A voltage. VBN, phase B voltage. VCN, phase C voltage. Some of the times they have asked the questions related to the pole voltage also. Okay, so that's why I'm representing here pole voltage differently. Okay, VAO, VBO, VCO, these are the pole voltages. Okay, so now yes, as I said, here we are having the two modes of operation. One is the 180-degree mode, second one is the 120-degree conduction mode. So my first question is, what should be our expectations from the three-phase inverter? Just in a single phase inverter, we discussed the expectation is like inverter should give the output voltage sinusoidal. Okay, in this case, yes, what should be our expectations? Inverter should give the balanced output, yes or no? Balanced three-phase output. What do you mean of the balanced three-phase output? Yes, the requirement is like all the three-phase voltages should be having the same frequency, same peak value, same RMS value, right? All the three line voltages should be having the same RMS value, same peak value, okay, as well as same frequency. All the three-phase voltages should be the phase displaced by 120 degree. All the three line voltages should be displaced by 120 degree from each other. Yes or no, right? So these are the requirements. Now let us, and one more important thing, the line voltage or the phase voltage nature or the waveform should be the sinusoidal one. These are the requirements or the expectations. But now let us discuss whether our practical inverter is fulfilling those requirements or those expectations or not, right? So let us discuss. So yes, let me write here 180-degree conduction mode. So the operation table for 180-degree conduction mode, let me write operation table. Yes. Interval and conducting switches. So we are having total 6 intervals. 1, 2, each interval is of 60 degree. So 60 into 6 is nothing but 360 degree, right? 4, 5, and the 6. Okay. So we are going to operate the switches like during interval 1, switch number 6 and switch number 1 will be in a conduction mode. Switch number 6, 561. It is a 180 degree. Na? So S5, S6, S1. This should be in on state. Interval 2, S6, S1, S2. We are going to turn on. During the third interval, it is like a S1, S2, S3 will be in a conduction mode. S2, S3, S4 during the fourth interval. During the fifth interval, S3, S4, S5, and during the sixth interval, S4, S5 and S6, and after this again it will move to the interval number 1. As I said, in the operation table we are having the 6 intervals. Each interval is of 60 degree. So 60 into 6 means what? 360 degree. That is a one complete cycle. Yes or no? Right? So 60 into 6. So that's why the 360 degree. So during the first interval, which 3 switches will be in a conduction mode? Switch number 5, switch number 6, switch number 1. During the second interval, switch number 6, 1 and 2. Third interval, 1, 2, 3. Similarly, fourth interval, 2, 3, 4. Fifth interval, 3, 4, 5, and similarly for the sixth interval. Okay. So during each interval, 3 switches will be in a conduction mode. Okay. Each switch conducts for 180 degree. So that's why it is known as a 180 degree conduction mode. Please check. I am saying each switch conducts for 180 degree. You can check switch number 1 is present here. Switch number 1 is present in the second interval also. Switch number 1 is present in the third interval also. But you can check 4, 5, and 6. Remaining 3 intervals, switch number 1 is not there in the conduction mode. Right? So switch number 1 is in a conduction mode only for 3 intervals. Each interval is of 60 degree. So 60 into 3 means 180 degree. Okay. So switch S1 conducts for 180 degree. Similarly, S2 you can check, S3, S4, S5, and similarly you can check for S6 also. Okay. So let me write, each switch conducts for 180 degree. Okay. Each interval is of 60 degree. Each interval is of 60 degree. Each interval is of 60 degree. Right? 3 switches will be in a conduction mode at a time. Okay. 3 switches conducts at a time. 3 switches conducts, right, at a time, or you can say simultaneously. So at a time, 3 switches will be in a conduction mode. Now let us discuss the circuit operation and waveforms. Okay, so we are going to draw the waveforms like VAN. Let me write here VAN. This is like, let me write it as omega t 0. Next, VBN, omega t 0. Similarly, VCN. Right. After this, we'll discussing about the VAB, VBC, VCA as well. Okay, and the pole voltages also. Okay, so let me draw here. Yes, we're having total how many intervals? 6 intervals. So this is first, second, third, fourth, fifth, and sixth, right? As I said, each interval is of 60 degree. Na? So can we write? Yes. This angle is nothing but pi by 3. 60 degree. Na? This angle is 2 pi by 3. This is pi. This one is like 4 pi by 3, 5 pi by 3, and 2 pi. Okay. So now let us discuss the circuit operation. This is like interval 1, 2, 3, 4, 5, and 6 interval. Okay. So during first interval, switch number 5, switch number 6, and switch number 1 will be in a on state, right? So you can check when switch number 5, 6, 1 are in a conduction mode. Switch number 5, 6, 1 are in a conduction mode. So switch number 5 we are going to turn on, that is trigger. Switch number 6 and switch number 1, right? These 3 switches are in a conduction mode. So you can check, it is like a positive plate of the supply through the S1 will be connecting to the terminal A, that is the phase A, right, of the load. Similarly, you can check through S6, the negative plate of the supply will be connected to the phase B, and phase C of the load will be connected through S5 to the positive plate of the supply. So equivalently, can we say that phase A of the load is connected to the positive plate of the supply, phase B through S6 to the negative plate, and phase C through S5 to the positive plate of the supply. Okay, so it is like phase A and C are connected to the positive plate of the supply, phase B is connected to the negative plate of the supply. Okay, so let me draw the equivalent circuit. Okay, during interval number 1, let me draw the equivalent circuit. Yes, interval 1, let me write interval 1. Yes, phase A and C are connected to the positive plate of the supply. Here we have the supply, it is a VS. Okay, so phase A, phase C, positive plate of the supply, and phase B to the negative plate of the supply. So we'll be having circuit like this: R. This is the your neutral point. Phase A here, phase C here, and phase B here. Yes or no? Please check. Equivalent circuit I have represented like this: phase A positive plate, phase C positive plate, phase B negative plate. This is the your star connected load, and this is the neutral point. Yes or no? Right? So now you can check. It is like R and R connected in parallel. Okay, so equivalently, yes, can we reduce this parallel combination with R by 2? Yes, so let me reduce the further circuit like this. R in parallel with R, so it is a R by 2 and it is a R as it is. So this is your VS. This is R by 2, here it is R. We are having a neutral point here. A and C are connected together now, so A and C are there and B is here. Yes or no? So please try to understand. From first, this interval 1 switches, these switches we have turned on. After that we got the, yes, like phase A is connected through S1 to the positive plate, phase B negative plate, phase C positive plate. Okay, so A and C positive plate, and after that B is negative plate, and in between A, B, C we are having a star connection. Okay, next again R connected in parallel, so I have replaced it with R by 2, and this is R. Now can we find the VAN? VAN means what? Which voltage represents the VAN? Yes, this voltage is equal to your VAN. Whether VAN and VCN both will be same or different? Definitely both will be same, na? Because phase A and phase C are connected to the same terminal. So VAN and VCN both will be same. Similarly, VBN I am saying VBN means B should be positive, N should be negative. This is nothing but your VBN. Yes or no? But in this circuit, if you check, current will flow like this, na? Right? So if the current is flowing like this into this circuit, can I say that VAN and VCN will be positive, but VBN will be negative? Because current is flowing in this branch, current is flowing in the downward direction. Current always flows from point of higher potential to point of lower potential. So from A to N, A and C connected together. So A to N current is flowing. So can I say that terminal A is at higher potential compared to the neutral point? Yes. So that's why your VAN is positive. But compared to the terminal B, N is at higher potential because current is flowing from N to B, na? Current is flowing from N to B. So that's why here VNB is positive, but VBN is negative. Please try to understand. Okay. Now simple, can we apply voltage division rule here in order to find the VAN, VBN, right? So let me write VAN by using voltage division rule I am saying. Okay. How to find VAN? VAN and VCN both will be same, na? Which is equal to what? R by 2, right? Upon R plus R by 2 into this voltage, right? VS. Total voltage into this resistor divided by addition of full resistor. That is nothing but your VAN, VCN. Okay. So which is equal to, you can write R by 2 upon 3R by 2 into VS. Right. So this can be written as 2 will get cancelled, RR will get cancelled. So can I write it as VS by 3? This is your VAN and VCN. What about the VBN? You can write VBN also. Let me write here VBN. I'm writing here VBN. Either you can do VS minus this thing, that will give you the VNB actually. So VBN will be negative. Okay. But let me first write the VBN. So VNB, let me write VNB. I'm writing VNB, right? So it is equal to R upon R plus R by 2 into VS, na? So it is like R upon 3R by 2 into VS, right? So it is equal to 2 by 3 VS. This is VNB, right? So if this is VNB, what about the VBN? So therefore VBN, let me write, therefore VBN is the negative of this na VNB. So it is a minus 2 VS divided by 3. So during the first interval, VAN is VS by 3, VBN is VS by 3, VAN is VS by 3, VCN is VS by 3, VBN is minus 2 VS by 3. Okay, so can we draw the plot? VAN VS by 3. Let me indicate VAN. It is a VS by 3. So it is like this. Yes. Suppose this step is like a VS by 3. This is a VS by 3. What about the VCN? VCN is also VS by 3. Na? So suppose this is also VS by 3. What about the VBN? We have written VBN is minus 2 VS by 3. Okay, minus 2 VS by 3 means suppose at this instant, this is like your minus 2 VS by 3, for example. Okay, this is during 0 to pi by 3. Second interval we are having S6, S1, S2 are in a on state. Now S5 we are going to turn off. We are going to turn off the S5. Okay, so either suppose if the switches are like MOSFET, then I am going to remove the VGS. Okay, so that your S5 will turn off, and newly added switch is S2. S6, S1, S2 on state. So S6, S1, S2. So S5 is off now, and newly added switch is your S2. So S6, S1, S2, S6, S1, S2 will be in on state. So you can check during this interval, phase A through S1 positive plate of VS, phase B through S6 negative plate of VS. What about the phase C? Phase C through S2 negative plate of the VS. So now during the second interval, phase A is a positive plate of the VS connected, and phase B and C are connected to the negative plate of the VS. Na? So equivalent circuit will be during the interval 2. Let me draw interval 2. The equivalent circuit, yes, phase A positive plate of the VS, and phase B and C. So A is like this, and B and C to the negative plate of the right VS. So it is like a B and C connected together. This is R and R. This is also R, and this is a phase A. Right? I am maintaining this star connection as it is. The only thing is I am moving these points A, B, and C, so that equivalent circuit, okay, whatever we discussed, right, that will be getting satisfied. You can check R connected in star only. Na? A is to the positive plate of VS, B and C to the negative plate of VS. Now what about this R and R? These are connected in parallel. Na? So equivalent will be R by 2. So can I represent this network like this is a R, here it is neutral point, and here it is a R by 2. Yes or no? This is a neutral point. This is a VS. Let me write here VS. Here it is a neutral point. Okay. This is a R. This is a R by 2. R in parallel with R, that is R by 2, right? Phase A is here, and phase B and C are connected here, right? Because B and C are short circuited. Na? Now, yes, can we find VAN, VBN, VCN? Yes. What is the VAN? You can apply voltage division rule. VAN is equal to R upon R plus R by 2. Na? So that is 3R by 2 into VS. So you can check it is equal to 2 by 3 into VS. This is VAN. VBN and VCN both are same. Na? Now my question is VBN, VCN positive or negative? Come on. VBN and VCN will be positive or negative? Negative, na? Right? VBN, VCN will be negative. Okay, because current is flowing from N to B. Okay. So actually VNB, VNC positive, but VBN, VCN negative. Okay. So it is a minus. If this is 2 by 3 VS, definitely it will be your VS by 3. Or you can use the voltage division rule. You will understand. Okay. So it is like R by 2 upon 3R by 2. Okay. So you will be getting minus VS by 3. So you can check interval 2 by 3 VS, and it is minus VS by 3. So second interval 2 by 3. This is like VS by 3, and next one more step 2 VS by 3. 2 by 3 VS means 2 VS by 3, and this is like minus VS by 3, and here it is like minus VS by 3. Okay, so this is the waveform during second interval. For the third interval, you can check during the third interval, switch number 1, 2, 3 are in on state. Na? So 1 is on, 2 is on. Now S6 is out. Na? Instead of S6, 3 is getting added. So 1, 2, 3. 1, 2, 3, right, are in a on state. So phase A positive plate of the VS, phase B, positive plate of the VS, phase C, negative. A and B are connected to the positive plate of the VS and C is connected to the negative plate of the VS. So let me draw. Yes, interval number 3. Interval 3, yes, we'll be getting equivalent circuit like this. Phase A, phase B, right? And here it is a phase C. This is VS, R. This is the neutral point, R. Phase A and B are connected together. Phase C, negative plate. Na? Again, this is RR parallel. Okay, so R by 2. Let me draw it as VS, R by 2, neutral point, and this is R. This is R by 2, VS. Right, so this is A and B, and here it is C. Now similarly we can write VAN is equal to VBN, okay, is equal to voltage division rule. You can use R by 2 upon 3R by 2 into VS. Na? So 2 cancel, R cancel, it is like a VS by 3. And what about the VCN? It is equal to minus 2 VS by 3. Minus 2 VS by 3. So you can check during third interval. VS by 3, VAN, VBN, and it is a minus 2 VS by 3. Okay, so VS by 3, VN and VBN are VS by 3. So this is VS by 3. And next VBN is also VS by 3. And VCN is minus 2 VS by 3. So it is like this. Okay, so these are for first 3 intervals I have shown. Similarly, you can check for remaining 3 intervals. We'll be getting the waveform like this. Minus VS by 3, minus 2 VS by 3, minus VS by 3. So this type of waveform will be getting, and again it repeats after 2 pi. Okay, so this waveform will be getting like this. Right. Okay, so let me indicate the pulse here or the step. This is VS by 3. This one is 2 VS by 3. This is minus 2 VS by 3. This is minus VS by 3. Similarly, here it is 2 VS by 3. Right? This is minus VS by 3. Okay. Similarly, this step is VS by 3. Okay. Minus 2 VS by 3. Minus VS by 3. This is 2 VS by 3. Okay, this is the VS by 3. Okay, so these are the phase voltage waveforms. Now, expectation was sinusoidal waveform, right? But you can check here whether we are getting the sinusoidal waveform. No, it is a stepped waveform. It is a stepped waveform. Okay. Now, but second expectation was, or the requirement was, there should be the phase displacement of 120 degree. Now you can check the phase displacement between VA and VBN. For the VAN, we are having waveform like VS by 3, 2 VS by 3, VS by 3. Now the same waveform is repeating in VBN after 2 intervals. Now you can check VS by 3, 2 VS by 3, VS by 3. Means whatever the waveform we are having from VAN, the same is repeating in VBN, but after 2 intervals. 2 intervals means what? It is a 120 degree. Na? So can I say that VBN is lagging to VAN by angle 120 degree? Yes. Similarly, you can check VCN and VBN also. In the VBN, we are having waveform like minus 2 VS by 3, minus VS by 3, plus VS by 3. So same waveform of VBN is repeating in VCN. After 2 intervals, na? After this point, you can check. After this point, minus 2 VS by 3, minus VS by 3, plus VS by 3. Okay. So can I say that VCN is also lagging to VBN by angle 120 degree? Okay. Means the mutual phase displacement between the phase voltages is 120 degree. Okay. This point is satisfied. Next, you can check the peak value of each phase voltage. Peak value here it is 2 VS by 3. Here it is 2 VS by 3. Here it is 2 VS by 3. Right. So we are getting the same peak value now. Right. Definitely. Nature is also same. Only thing is they have shifted by 120 degree. We will be getting the RMS value also same. We will be getting the RMS values also same. Right. Now frequency You can check, this is like after 6 intervals, one cycle is complete. Na? After that, again, the same cycle will repeat. So here from this point to this point, it is like a periodic time for the VAN, same periodic time for VBN, same periodic time for VCN. So frequency is also same, right? Means apart from sinusoidal, all other requirements are fulfilled. All other requirements are fulfilled. Okay. They have asked the question, the nature of phase voltage waveform in 180 degree square wave mode. Okay. It is a stepped waveform. It is a stepped waveform, right? So, so phase voltage is a stepped waveform. Phase voltage is stepped wave. Right. Now these are the waveforms of phase voltage. Now can we draw the waveform of line voltage? Yes, we can draw. Let me add the page here. So line voltage waveforms, right? So line voltages are VAB, VBC, and VCA, right? VAB, VBC, and VCA. So intervals we are having like pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and 2 pi, right? So okay, let me indicate here pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and 2 pi. Okay, so how to find the VAB? I'm writing VAB is equal to, it is a VAN minus VBN. That's it. Okay, VBC is equal to VBN minus VCN, and VCA is equal to VCN minus VAN, right? So can we find the VAB waveform? Yes, VAN minus VBN. We're having a VAN and VBN waveform here. So during the first interval, you can check VAN minus VBN. It is a VS by 3 minus of minus 2 VS by 3. So can I say that it is VS by 3 plus this 2 VS by 3? That is a 3 VS by 3. That is nothing but VS. Okay. So VAB is equal to VS. I'm writing it as a VS here. This width is VS, right? Next, VAB during second interval, it is a 2 VS by 3 minus this VS by 3. 2 VS by 3 minus of minus VS by 3. So it is like a VS again. So we'll be getting VS only. Next, during the third interval, you can check VS by 3 and this is also VS by 3. So VS by 3 minus VS by 3, 0 na? So we'll be getting here 0. Third interval. Fourth interval, minus VS by 3 minus 2 VS by 3. So it is like minus VS na? So we'll be getting here it is minus VS. Similarly, you can check here fifth interval, minus 2 VS by 3 minus VS by 3. So it is like again minus VS. And in the last interval, it is a minus VS by 3 and it is also minus VS by 3. So subtraction will be 0 na, right? So it will be 0. Is this clear? So we're getting this type of waveform for VAB. It is like a quasi square wave na? Pulse width is 120 degree. In between 60 degree, 60 degree, we are having 0. Okay, so it is like a quasi square wave. Next, can we draw the waveform for VBC? Yes, VBC waveform. VBN minus VCN. Let us check. Minus 2 VS by 3 minus VS by 3. So it is like minus VS, right? VBC is a minus VS. Second, minus VS by 3 minus VS by 3. So minus VS by 3 minus of minus. So it is a 0. Okay. Third interval you can check. Minus VS by 3 minus of minus 2 VS by 3. Okay. VS by 3 minus of minus 2. So it is like VS. So similarly, you can check for remaining. It will be like this, and again it will be same thing will be repeating here. Okay, so this is VBC. Similarly, we can draw for VCA also. VCA means VCN minus VAN. Na? So it is VS by 3 minus VS by 3 means what? 0. So it is a 0. Next, minus VS by 3 minus 2 VS by 3. So it is minus VS. Let me draw here. It has a minus VS. Similarly, you can check for remaining. It is minus VS, 0, plus VS, and like this waveform will be getting. Okay, so let me write here. This pulse is VS. This is like minus VS, VS, right? This is a minus VS, minus VS, and here it is a plus VS, right? Okay, so now expectation was line voltage should be sinusoidal, but whether these are sinusoidal? No. Nature of the line voltage is a Cauchy square wave. Nature of line voltage is Cauchy square wave. Next, you can check the phase displacement. Phase displacement between the two line voltages. Let us consider VAB, VBC, right? You can check whatever the waveform we're having for VAB, VS, VS, 0, minus VS, minus VS. Same is repeating in VBC after two intervals. Now, this is first interval, this is second interval. So VBC lagging to VAB by 120. Similarly, you can check VCA, VBC. You will be getting the mutual phase displacement of 120 degree only, right? Between the line voltages. So let me write here. Nature of line voltage. Line voltage is Cauchy square wave. Cauchy square wave. Cauchy square wave. Is this clear? Phase voltage was stepped waveform. This one is a Cauchy square wave. This one is a Cauchy square wave, right? Peak value you can check. It is VS. It is also VS. This is also VS. Okay. So apart from sinusoidal, all other requirements are fulfilled. Na? Peak value is same. You can check RMS value also. You will be getting the same only, right? Because 120 degree positive, 120 degree negative, remaining 120 degree 0. Same for remaining two line voltages also, right? So RMS value you will be getting the same, right? Next. Now, can we draw the pole voltage waveform? Pole voltage waveform is VAO, VBO, and VCO, right? So let me draw the pole voltage waveform. Yes, here I'm drawing pole voltage waveform. Right, pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and 2 pi, right? So let me write here pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, 2 pi. Okay. So 0 to pi by 3. Please check VAO. So how to find the phase voltages? Please listen. Phase voltages means potential difference between A and O. Na? Suppose and phase, this terminal A is connected to this line or this line either through S1 or S4. Suppose if S1 is in a on state, can I say that VAO means voltage between these 2 points is nothing but VS by 2? Please try to understand this thing. When S1 is in a conduction mode, simply you can apply KVL to this loop. This is A is nothing but this is also A. Na? So VAO is nothing but this is plus, this is minus here. Okay. So apply KVL to this loop. You will understand it is like plus VS by 2 minus VAO is equal to 0. So VAO is VS by 2. Means when S1 is in on state, VAO is VS by 2. But suppose instead of S1, when S2 is in on state, sorry, when S4 is in on state, so it is like this is plus will appear at the O, minus will appear at the A. Na? So can we apply KVL to this loop? It is a plus VAO plus VS by 2 is equal to 0. So VAO is equal to minus VS by 2. So check here, while finding the VAO, VBO, and VCO, we need to simply check whether the switch in the upper group is in a on state or the switch in a lower group is in a on state. If the switch is in a upper group is in a conduction mode, then your respective pole voltage will be positive and that value will be Vs by 2. If the switch in a lower group will be in a conduction mode, then the respective pole voltage will be negative and the value will be minus Vs by 2, right? So now you can check. Here we are having S1 is in a conduction mode from first, second and third. So your VAO will be Vs by 2. VAO will be Vs by 2. So let me draw here. For first three intervals, VAO is equal to Vs by 2 only. This is Vs by 2. Because S1 is in a conduction mode, na? S1 is in a conduction mode. For the next three intervals, if you check, for the next three intervals, here it is S2. For the next three intervals, S4, 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 right? Because with S1, we are having second is S4, na? So either S1 is in on state or S4 is in on state, right? As per operation table. So when S4 is in on state, you can check S4, S4, S4. So it is like for remaining three intervals, can I say that VAO is equal to minus Vs by 2? Yes. So it is a minus Vs by 2. So we'll be having, this is like a minus Vs by 2. So this type of waveform will be getting minus Vs by 2. Okay. This is Vs by 2 and here it is a minus Vs by 2. Similarly, can we write VBO? For VBO, yes, we are having switches S3 and S6. We need to check S3 and S6. Okay. So check when S3 is in a on state, VBO is Vs by 2. When S6 is in on state, VBO is minus Vs by 2. Okay. So check the operation table. S3 and S6. Here it is S3, S3, S3. That is interval number 3, 4, and 5. 3, 4, 5. Interval number 3, 4, 5. 1, 2, 3. So it is 3, 4, and 5. So the waveform will be like this. And for remaining two intervals, the next switch. Okay. So this is like a Vs by 2. And this is like a minus Vs by 2. Okay. Similarly, we can check for the third one, that is the VCO. Here it is VCO. VCO will be equal to Vs by 2 when S5 is in a conduction mode. When S2 is in a conduction mode, VCO will be negative, that is minus Vs by 2. So check for S2 and next S5. Okay, S2 how it is? You can check S2, here it is present, here it is present, here it is present. Means second, third, and fourth interval. Second, third, and fourth interval. Okay, so second, third, and fourth interval. So it is a Vs by 2. For remaining intervals, it will be minus Vs by 2. So this voltage is Vs by 2. This voltage is minus Vs by 2, right? So here we are having the pole voltages. So what is the nature of pole voltages? It is a square wave, no? Right? It is a square wave. Pole voltage is a square wave. Square wave, right? So please keep it in mind. Phase voltage, it is a stepped waveform. Line voltage, quasi square wave, and pole voltage is a square wave. Okay, pole voltage is a square wave. Now we are going to derive the expression of RMS value of phase voltage, RMS value of line voltage. Okay, so let me write. We'll discuss all your questions at the end of the session. Okay, so RMS value of phase voltage, let me write. RMS phase voltage. So let me write it as VAN RMS, right, which is equal to, so you can check VAN waveform, right? 330. Yes, VAN waveform you can check here. So we're having Vs by 3, 2 Vs by 3, Vs by 3, same pulse in the negative also. So you can take RMS value either over 0 to pi or 0 to 2 pi. In both the ways, you'll be getting the same answer. Okay. So let me write VAN RMS is equal to 1 by pi. I'm writing it as 1 by pi. Integration from 0 to pi by 3 Vs by 3 square d omega t plus integration from pi by 3 to 2 pi by 3. It is like a 2 Vs by 3 bracket square into d omega t plus integration from VCO. Okay, okay, just a minute. Let me check. VCO 234 VCO. Okay, 135. Correct. That should be reverse, right? Okay. 2 is conduction 234, and in the circuit 2 is here, right? So thank you. So VCO should be reversed actually. Yes. So here it is like this, right? So this is minus Vs by 2, and here it is a plus Vs by 2. Correct? So next. Yes. So 2 pi by 3 to pi to next one is the 2 pi by 3 to pi. Okay, so let me write this integration here. Integration from 2 pi by 3 to pi. It is Vs by 3 square into d omega t to the power 1 by 2, right? 1 by 2. Okay. So we can write it as, can we take Vs by 3 outside? Yes, so it is a Vs by 3 root pi. This pi I have taken outside, Vs by 3 also I have taken outside. So into it is like a, we can write it as a, I'm directly writing, it is a pi by 3 plus, that will be 4 into pi by 3 plus, here it is a pi by 3 to the power 1 by 2. So if you check, it is equal to Vs upon 3 root pi into 4 pi by 3, 5 pi by 3, 6 pi by 3. 6 pi by 3 means 2 pi to the power 1 by 2. So if you check, VA and RMS is equal to pi will get cancelled out. So it is root 2 Vs by 3, na? Root 2 Vs by 3. So RMS phase voltage is equal to VA and RMS is equal to root 2 Vs by 3. Root 2 into Vs divided by 3, na? Root 2 Vs by 3. This is your VA and RMS. Okay. So similarly, you can check for VB and RMS, VC and RMS, you will be getting the same value, right? Next, can we write the line voltage RMS value? RMS line voltage. RMS line voltage. Yes. Let me write VAB RMS. VAB RMS. So for that, please check VAB waveform. Here it is. 0 to pi, whatever the waveform we're having, same is repeating from pi to 2 pi. Only thing is negative. So I am finding the RMS over pi. Okay. So it is like 1 by pi integration over 0 to 2 pi by 3 Vs square. Okay. So 1 by pi integration from 0 to 2 pi by 3 Vs square into d omega t to the power 1 by 2. So it is equal to Vs by root pi into under root 2 pi by 3. Na? So you can check, pi will get cancelled out. So it is like root 2 Vs by root 3. Okay. So root 2 by 3 into Vs. This is your VAB RMS. Root 2 by 3 into Vs. Okay. So you can check, if we multiply the phase voltage with root 3, we'll be getting the line voltage. Yes or no? Because the star connection, in the star connection, we know line voltage is equal to root 3 into phase voltage. You can simply multiply this with the root 3, you will be getting root 2 by 3 into Vs. Okay, so line voltage. Next, so this is the phase voltage and line voltage RMS values. What about the load power? Can we find the load power? Yes, load power. Output side is AC, na? So how many phases we are having? We are having the 3 phases. Okay. So load power is equal to 3 into VPH RMS into IPH RMS. So it is equal to 3 into what is VPH RMS? Root 2 into Vs by 3. Root 2 into Vs divided by 3. Into what is IPH RMS? Load is resistive now. So let me write it as root 2 into Vs divided by 3R. So can we write it as 3 will get cancelled out. So it is like 2 Vs square divided by 3R. Right? This is your P0. That is the load power. That is the load power. Right? Next, can we draw? Yes. Now, can we draw the waveform of switch current? Switch current waveform, can we draw? Yes. IS1 switch current. Let me draw switch current waveform. Let me draw the IS1 waveform. We're having total 6 intervals: 1, 2, 3, 4, 5, and 6. Okay, so pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and 2 pi. Okay, so now IS1 waveform, you can check operation table. During the first 3 intervals, only S1 is in on state. Na? After the remaining 3 intervals, S1 is in off state. So therefore, for remaining 3 intervals, what about the waveform of IS1? Definitely it will be 0 because switch 1 is in off state na, during last 3 intervals. For the first 3 intervals, what is the IS1? What will be the value of IS1? If you check the circuit diagram, you will understand. IS1 means current flowing through the switch 1. That is the IS1. So can I say that current, whatever the current which is flowing through this switch is nothing but the current which is flowing through the phase A of the load? Na? Yes or no? Right? So can I say that IS1 is nothing but phase A current of the load? And that current, you can check how to find the phase current of the load. That is phase voltage of the phase A, that is the VAN divided by R. Are you getting this point? Okay, I'm right. I'm saying that yes, when S1 is in on state, at that time this current is nothing but IS1. Again, the same current is flowing through this phase, na? Right? So can I say that the current in this phase is nothing but your VAN divided by R? Okay. So for the first 3 intervals, we need to check the VAN waveform. For the first 3 intervals, VAN waveform is like this: Vs by 3, 2 Vs by 3, and Vs by 3. So therefore, how is the waveform of your IS1? It is like Vs by 3R, 2 Vs by 3R, and Vs by 3R. Are you getting the point? Okay. So let me draw the waveform. It is like Vs by 3R, 2 Vs by 3R, and again Vs by 3R. Right? So this is like Vs by 3R. Here it is 2 Vs by 3R, and this one is again Vs by 3R. Okay, so now can we find the RMS value of this waveform? Yes, IS1 RMS. Let me write IS1 RMS is equal to 1 by 2 pi. Now 0 to 2 pi, we're having the one complete cycle. Okay, so 1 by 2 pi. In that, we're having the 3 intervals. Na? So let me write directly here. Integration from 0 to pi by 3. It is like a Vs by 3R bracket square into d omega t, plus integration from pi by 3 to 2 pi by 3. It is 2 Vs by 3R bracket square into d omega t, plus integration from 2 pi by 3 to pi. It is again Vs by 3R bracket square to the power 1 by 2. No? Again, we can take Vs by 3R outside. Vs by 3R we can take outside. So let me write here. Therefore, IS1 RMS is equal to Vs by 3R into root 2 pi. Right? I am taking this root 2 pi also outside. Right? So into, it will be like pi by 3 plus 4 pi by 3 plus pi by 3. To the power 1 by 2. So it is like a Vs upon 3r into root 2 pi into, this is also root 2 pi, na? This will get cancelled out. So it is like Vs by 3r. This is your IS1 RMS, right? IS1 RMS, right? So waveform is important. How to draw the waveform of IS1? Please try to understand this thing. Okay. Next, can you find the IS RMS? IS RMS. IS RMS. How it will be? Let me draw RMS value of source current or the source current waveform. Let us first draw the source current waveform. And after that, we will discuss the how to find the RMS value. Okay. So IS omega t. We're having 6 intervals, right? Pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and 2 pi, right? So we're having the intervals. So how to draw the IS waveform? So please try to understand here. Yes. During each interval, we're having the circuit. For the first interval, we're having equivalent circuit like this. IS means this current, na? Source current. Again, we have reduced this circuit to like this. So here it is IS now. Yes or no? Now our IS is like this. So you can check in every interval, we are getting in the second stage, we are getting this type of circuit only, Vs, R and R by 2 series. Means across Vs we are getting R and R by 2 na. Similarly, you can check in the first interval. Second interval also we are getting Vs in series with or across Vs, R and R by 2 are connected. So this is like your IS. During third, you can check, this is the IS, third interval, R and R by 2 connected in series, and that series combination will be connected across Vs. So my question is, during first interval, second interval, third interval, whether the IS will be same or different? It will be same, na? Because total voltage is Vs and resultant resistance also same. It is R plus R by 2, that is 3R by 2. So what is IS? Vs upon 3R by 2. This is during third interval. During second interval, what is IS? IS is equal to Vs upon this addition of these two resistors. These two resistors are again R plus R by 2 means 3R by 2. During the first interval also you can check, IS means Vs upon this resistor. It is R plus R by 2 na? Means in every interval, in the second step, what we are getting? We are getting this type of circuit only na? R and R by 2 series. R and R by 2 series. R and R by 2 series. So IS value in all the intervals, it will be same only, right? You can check for fourth interval, fifth interval, sixth interval also. You will be getting IS is same. And what is that value? IS is equal to Vs upon R plus R by 2. That is 3R by 2. Okay, so let me write here IS. Yes, Vs upon IS is equal to Vs upon 3R by 2. That is nothing but 2 Vs by 3R. So IS waveform will be getting, it is a constant current waveform and having the magnitude of 2 Vs by 3R. 2 Vs by 3R. Because in each interval across Vs, we are having the same impedance, we are having the same resistance. Okay, that is the that is also R plus R by 2 na. So that's why IS is equal to Vs upon 3R by 2. That is 2 Vs by 3R, right? So this is your IS. So what about the IS RMS? Very straightforward. IS RMS, which is equal to IS average na, which is equal to 2 Vs by 3R. 2 Vs by 3R. Is this clear? Right? 2 Vs by 3R. Okay. So this is about the circuit analysis. Right? Okay. So this is about this circuit analysis of 180-degree conduction mode. Now we are going to derive the expression of Fourier series, okay, of phase voltage, line voltage, right, and as well as our pole to pole voltage, okay, pole voltage. So let me write here first. We will extend class till 9:30. So, Fourier series expression. 347. Here it is 347. Right? Okay. So sir, in load power there won't be 3 in denominator. Where you are saying in load power. No, this 3R is there, na? Yes or no? Right? So that's why the 3. Yes, Prajit.
Yes, go. While we were calculating RMS line voltage, that we calculated under root 2 by 3. That complete under root.
Okay. No, this is root 2 VS by 3, na?
Yes, sir.
It's RMS phase voltage.
Okay.
Line voltage is root 2 by root 3.
Yeah, sir. Got it.
So it is root 2 VS by 3. So that's why root 2 VS by 3 and this is R, right?
Okay.
So it is okay, right? Next, now let us discuss the Fourier series analysis. Okay. Fourier series expression. So let us first write for which current denominator root 3, where you are saying right. Okay, we'll discuss later on. So Fourier series expression, let me put the heading phase voltage waveform. Okay, phase voltage. Waveform. So let me redraw that phase A voltage waveform. It is like this, VAN. We're having 6 intervals, 1, 2, 3, 4, 5, and 6. Okay, pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and 2 pi. Okay, so we're having the steps like this: Vs by 3, 2 Vs by 3, Vs by 3, minus Vs by 3, minus 2 Vs by 3, and again it is a minus Vs by 3, right? So this is 2 Vs by 3. This is Vs by 3. Here it is minus 2 Vs by 3. Okay. So now my question is whether this VAN waveform is a even or odd signal. Come on. It is a even or odd? Odd, right? So AN will be 0. A0 by 2 average value will be 0. Okay. So let me write here directly. Yes. Average value of VAN is equal to A0 by 2 is equal to 0. Okay. As VAN is an odd function. So therefore AN is also equal to 0, right? AN is also 0. So only thing we need to find is BN only, na? Right? So how to find BN? Let me write. BN is equal to 1 by or 2 by 2 pi. Let me write it as 2 by 2 pi into integration from, you can check around 6 integrations, right? 0 to pi by 3 Vs by 3 into sine of n omega t into d omega t. This is the one. Integration from pi by 3 to 2 pi by 3. It is a 2 Vs by 3 into sine of n omega t d omega t plus integration from 2 pi by 3 to pi, value is Vs by 3 na, into sine of n omega t into d omega t plus integration from pi to 4 pi by 3. What is value? Minus minus Vs by 3 into sine of n omega t into d omega t plus integration from 4 pi by 3 to 5 pi by 3. What is value? Minus 2 Vs by 3 into sine of n omega t into d omega t, and the last interval integration from 5 pi by 3 to 2 pi. It is again minus Vs by 3 into sine of n omega t into d omega t, right? So now we need to simplify these expressions, okay, these integrations. So it is like 1 by 2 pi means 1 by pi. So let me write here, therefore Bn is equal to 1 by pi, and in that also can we take Vs by 3, Vs by 3? In every integration we're having Vs by 3 there. So can we take it outside? Yes. So it is like Vs by 3 pi. Vs by 3 pi into, in the bracket, yes, it is like a integration of sine of n omega t. It is a minus cos of n omega t divided by n is there. Here also you will be getting integration is like minus cos of n omega t divided by n. Means in every integration, after taking the integration, if you check, we'll be getting divided by n term na. So can I take that divided by n also outside? Yes. So I'm taking divided by n also outside. So it is like a 2 Vs by 3n pi. 3n pi. Are you getting the point? Why I have taken here n outside, right? So that n is like minus cos of n omega t divided by n. So divided by n I have taken outside. So now integration of sine is minus cos. Okay. So it is like let me write here. Yes, minus cos of n omega t, limit 0 to pi by 3. 0 to pi by 3. Yeah. Yes, 0 to pi by 3 plus, here it is 2 times na, so we need to take 2 there, so that's why it is 2 into, I am writing minus cos of n omega t, right, limit pi by 3 to 2 pi by 3 plus, here it is Vs by 3 were taken outside, so it is like a minus cos of n omega t. Let me write here minus cos of n omega t, limit 2 pi by 3 to pi. Next you can check, here it is minus already present, so integration of sign is minus cos, so that will become plus. So I'm writing plus cos of n omega t, limit pi to 4 pi by 3 plus, next we are having this integration, okay, it is 2 there, okay, so let me take 2 outside, 2 into cos of n omega t, limit 4 pi by 3 to 5 pi by 3, and plus last thing is cos of n omega t, 5 pi by 3 to 2 pi, okay. So this is the one thing. So we're having total 6 integrations. You can check we're having 6 brackets. Okay. So let me write therefore Bn. I'm writing it as Vs upon 3n pi into minus cos of n pi by 3, minus cos of n pi by 3. And this is minus minus plus. So it is a plus, cos 0 means 1 na? After putting the lower limit. So plus 2 into cos of n pi by 3 minus 2 into cos of upper limit 2n pi by 3 plus, for this term it is like cos of 2n pi by 3 minus cos of n pi, okay, plus cos of 4n pi by 3 minus cos of n pi, okay. So for this term plus, let me write for the here 2 into cos of 5n pi by 3 minus 2 into cos of 4n pi by 3 plus cos of 2n pi. Okay, 2n pi directly I'm writing 2 pi n, that is 2n pi minus cos of pi n pi by 3. So you can check which terms will get cancelled out. Here it is, we are having minus cos n pi by 3. Here it is a plus 2 cos n pi by 3, means this minus, and out of these two, one will get cancelled out. Okay, here it is minus 2 cos of 2n pi by 3. Here it is plus, this is plus na, cos of 2n pi by 3, means one will get cancelled out. Next, cos of 4n pi by 3, and here 2 times, so one will get cancelled out. Okay, next thing is, here it is pi n pi by 3, here it is 2 times, so this will get cancelled out. Okay, so we'll be having the terms like, you can check cos of n pi by 3 minus cos n pi minus cos n pi, so it is like minus 2 into cos n pi. What about the cos of 2n pi? Cos of 2n pi, yes, you can check, n is equal to 1, cos 2 pi, it is a 1. N is equal to 2, cos 4 pi, it is a 1, right? N is equal to 3, so cos 2n pi is equal to 1 only. Okay, so I'm going to replace this term with a 1. So let me write here bn. So therefore bn, yes, therefore bn is equal to Vs upon 3n pi into, let me write it as, this is 1, this is also 1, so it becomes 2. So 2 minus, you can check, cos of n pi minus cos of n pi, so it will become 2 times cos of n pi. 2 times cos of n pi. Okay, next, cos of n pi by 3. Okay, cos of n pi by 3 plus cos of n pi by 3. Next, minus cos of 2n pi by 3 minus cos of 2n pi by 3. Okay, next, this minus n pi were taken already, plus cos of phi n pi by 3 plus cos of phi n pi by 3. Okay, and next term is minus cos of 4n pi by 3. Okay, minus cos of 4n pi by 3 minus cos of 4n pi by 3. Okay, so now we need to find the bn value for various values of n. Okay, yes, yes, yes. Okay, yes. So now we need to find the value of bn for various values of n. Okay, so let me check. For n is equal to 1, for n is equal to 1, come on, open your calculators, check, put n is equal to 1 and tell me what answer you will be getting. It is like Vs upon 3 pi into, what about this bracket? Check for this bracket. At the end we will be drawing very beautiful conclusion. Okay, yes, how much? Yes, it is a 6 we are getting, right? So here it is a 6. So you can check, it is like a Vs upon 2 Vs by pi. Okay, this is like a 2 Vs by pi for n is equal to 1. Yes or no? Similarly, check for n is equal to 2. For n is equal to 2. Yes, what is bn? It is Vs upon, you can check, 6 pi na, into, check for this bracket. Check for n is equal to 2. Don't sit idle. Okay, Yes, it is 0. N is equal to 3. Come on. Vs upon 9 pi into this bracket. Check for n is equal to 3. You will be getting 0, right? Zero. N is equal to 4. You will be getting 0. Please check. N is equal to 5. Please check Bn value. It is like a Vs upon 15 pi into this term. For n is equal to 5. Yes, this bracket is 6 na. So n is equal to 5. We are getting it is like a 2 Vs divided by 5 pi na. Yes or no? Right? Similarly, check for n is equal to 6. We will be getting 0. N is equal to 7. We will be getting it is a 2 Vs by 7 pi. Check once for n is equal to 7. Yes, 7 pi. N is equal to 8. We will be getting 0. N is equal to 9. You will be getting 0. N is equal to 10. You will be getting 0. Right? Let me write. N is equal to 10. Bn is 0. Please cross check it. N is equal to 11. You will be getting Bn is equal to 2 Vs by 11 pi. 2 Vs by 11 into pi. Right? So similarly, you can check n is equal to 12. You will be getting 0. For 13, you will be getting 2 Vs by 13 pi. 14 0, 15 0, 16 0, 17 2 Vs by 17 pi, etc. Okay. So right. Yes, correct. Now, so here from this, can we say that you can check a0 by 2 is already 0. An is also already 0 now. The only thing is your expression, Van expression, it depends on only Bn value now. And in that also you can check Bn is 0 for all even values of n. 8 is 0, 6 is 0, 2 is 0, 4 is 0, right? Means all even harmonics are absent. Second thing, only even are absent. No, you can check for n is equal to 3 also. Bn is 0 na. N is equal to 6. It definitely it is a even. No problem. N is equal to 9 also. It is 0. You can check for n is equal to 15. You will be getting 0. The meaning is all even harmonics and the triple n harmonics are also absent. Okay. Means let me write here. Therefore, Bn is equal to 2 Vs divided by n pi for n is equal to 1, 5, 7, 1, 5, 7, 11, 13, 17, etc. And it is equal to 0. Bn is equal to 0 for all even n and triple n. Triple n. Triple n means what? Triple n is nothing but 3 into n. Triple n is nothing but simply 3 into n. You can check n is equal to 1, it is a 3. N is equal to 2, it is 6. N is equal to 3, 9. N is equal to 4, 12. N is equal to 5, 15. Means all this 3, 6, 9, 12, 15, 18, 21, etc. All these are the triple n harmonics. All these are the triple n harmonics. Okay. So in our case, Bn is 0 for all even values of the n, and at the same time triple n values. Okay, triple n values of the n. Okay, so Bn is 0. Now can we write the expression Van? So therefore Van is equal to summation over n is equal to 1, 5, 7, 11 and so on, right? And so on. It is a value 2 Vs by n pi na. So 2 Vs divided by n pi into sine of n omega t into sine of n omega t, right? So further we can write it as till infinity. Yeah? Further this can be written as therefore Van is equal to summation over n is equal to 6k plus minus 1 up to the infinity, 6k plus minus 1 up to the infinity. What is value? 2 Vs by n pi into sine of n omega t, where k is equal to 0, 1, 2, 3, so on. You can check. I have represented these harmonics now with this in this term 6k plus minus 1. You can check if k is 0. If k is 0, it is like 6 into 0 plus minus 1. So 6 into 0 means 0. So it is like 0 plus 1, 0 minus 1. 0 plus 1 is nothing but n is 1 na. So whether fundamental is present? Yes, fundamental is present, right? Next, k 0. So it is like 0 plus 1, 0 minus 1 na. So minus 1, n is equal to minus 1. Whether in the harmonics we are having the negative order? No. So n is equal to minus 1 is not having any meaning. It is a meaningless. Second, you can check if k is equal to 1. Put here k is equal to 1. It is 6 into 1 plus minus 1. 6 into 1, that is 6. 6 plus 1, 6 minus 1. 6 plus 1 is 7. 6 minus 1 is 5. So you can check after fundamental we are having directly fifth harmonic. And after that we are having directly seventh harmonic. Okay. K is equal to 2. You can put 12 plus minus 1. 12 minus 1, 11. 12 plus 1, 13. Okay. So we'll be having after 7, 11. After 11, 13. Right. So like this we can represent. So this is your Van. Similarly, can we write the expression of Vbn? Right. Also, Vbn is equal to same thing. N is equal to 6k plus minus 1 up to the infinity. It is 2 Vs divided by n pi into sine of, let me write it as n into omega t. N into omega t minus, what is the phase difference between Va and Vbn? 120 degree, na? Right? So 120 degree is like a 2 pi by 3, right? 2 into pi by 3. Similarly, we can write Vcn is equal to summation over n is equal to 6k plus minus 1 up to the infinity. It is 2 Vs divided by n pi into sine of n into omega t plus 2 pi by 3. Na? This is leading to Van by angle 120 degree. So I am adding here plus 2 by 5. Vbn was lagging to Vn. So angle is minus 2 pi by 3. Okay. So these are the expressions of Fourier series expressions of phase voltages, right? That is the phase voltages. Now we are going to write the Fourier series expression of line voltage. Okay. Line voltage. Yes. Yes. So please try to understand. They ask the question in a 180 degree conduction mode, in a phase voltages, all even and triple n harmonics are absent. All even and triple n harmonics are absent. Okay. Next, let us do the Fourier series analysis of line voltage waveform. Okay. So line voltage. Fourier series expression for line voltage. So let us write for VAB. Okay, VAB. How is the waveform of VAB? If you check, we have drawn the VAB waveform. Yes, here it is. 0 to 2 pi by 3 Vs, and after that 0 and again minus Vs. Okay, so waveform is like this. Yes. Yes. So VAB the waveform is like this. Here it is 0. This is like your 2 pi by 3. This is a pi. 4 pi by 3, 5 pi by 3, and here it is 2 pi, right? 2 pi. Now this is a Cauchy square wave, na? Right? Now whether it is a even or odd, yes, same expression as that of the single phase semi converter. Okay, but let us discuss here, right? In short, we will complete it. Yes. Yes, it is neither even nor odd, na? So what we are doing generally, we are shifting it by 30 degree, na? Right? So let me shift it by 30 degree. Okay. So that this 30 degree means this 60 degree will be getting it as a 30 degree gap here. Okay. So now let me write it as, or in the semi converter also we're having. Yes, do you want to say something, Mahinder? Yes. Okay. Yes. Okay. Okay. So let me shift this waveform by 30 degree so that we'll be getting it as a VAB dash, na? So omega t 0, 2 pi by 3, pi, 5 pi by 3, and this is 2. Okay. So after 30 degree, so it is like a pi by 6 here. This will be like your pi by 6 plus 120 degree, na? Sorry, yes. This will be like a 5 pi by 6. Next, we are having this type of waveform. Till this instant, it is like 7 pi by 6. And next, the negative pulse. Till which instant this will be 11 pi by 6. And this will be like a 2 pi. Yes or no? You can check. 0 to pi by 6. 30 degree gap is there. At the end also 30 degree gap. Right? In between, this is a pi. Before pi 30 degree, after pi 30 degree. Now you can check this waveform. It is a even or odd signal. It is a, yes, odd function, na? Right? It is an odd function. What is this magnitude? This magnitude is, I think it is a Vs. Okay. This is also minus Vs. Right? We check once. Yes, Vs were correct. So definitely this is also Vs. This is also minus Vs. Now, can we do the Fourier series analysis of this waveform? Yes. Shall I write the answer directly? Because the same thing we already discussed. Yes, direct. Very good. Huh? Let me write the answer directly. Okay. So, therefore, I am writing it is VAB is equal to summation over n is equal to, yes, correct. But please try to understand how this cos of n pi by 6 is getting added. That is important. Please try to simplify at your own, because the same expression, same waveform we have already analyzed in the semi converter. Right? 4 Vs by n pi into cos of n pi by 6 into sine of n into omega t plus pi by 6. Okay. Similarly, you can write VBC summation over n is equal to 1357 up to the infinity 4 Vs divided by n pi into cos of n pi by 6 into sine of n into omega t. This is difference between these two line voltages is equal to 120 degree. Na? So it is 30 degree leading. So that's why it is minus pi by 2 is sufficient. Okay. To create a phase difference of 120 degree. Right. So minus. Similarly, VCA summation over n is equal to 1357 up to the infinity 4 Vs divided by n pi into cos of n pi by 6 into sine of, yes, this can be written as n into omega t plus 5 pi by 6. Okay. Right. So these are the Fourier series expressions of line voltage. Next, can we write for the phase voltage Fourier series expression? It is a 180 degree square wave na? Fourier series expression of pole voltage. Expression of pole voltage. You can check the pole voltages we are having. Yes, we have drawn here. Yes, VAO, VBO, VCO, right? So you can check the phase displacement 120 degree. Here it is also phase displacement is of 120 degree. Okay. So VAO, it is a 180 degree square wave, Vs by 2 and minus Vs by 2. So let me write here. Yes, VAO waveform. This is omega t 0, 0 to pi Vs by 2. Next minus Vs by 2 and same type of waveform. So this is Vs by 2. This is like a pi and this is a minus Vs by 2. This is a 2 pi. Yes, whether what is the Fourier series expression of this type of waveform? VAO is equal to summation over. It is like a output voltage of single phase half bridge inverter, na? Right? Vs by 2 minus Vs by 2, right? So summation over n is equal to 1357 up to the infinity. Okay, up to the infinity. It is like we can write it as a 2 Vs divided by n pi into sine of n omega t into sine of n omega t. Is this clear? This is your VAO. Same method of your single phase half bridge inverter. Same method of the single phase half bridge inverter, right? Yes. Next. Similarly, you can write VBO also. VBO. Let me write VBO. Summation over n is equal to 1357 up to the infinity. It is a 2 Vs divided by n pi into sine of n into omega t minus 2 pi by 3. And VCO is equal to summation over n is equal to 1357 up to the infinity 2 Vs by n pi into sine of n into omega t plus 2 pi by 3. Right? So this is about the Fourier series expressions of pole voltages. Pole voltages. Now my question is, in the pole voltages, which harmonics are absent? Even harmonics are absent. Only odd harmonics are present, right? Next, what about the line voltages? In the line voltages, which harmonics are absent? Come on. Whether the, yes, you can check cos of n into pi by 6. Okay. So for n is equal to 3 here, you can check for n is equal to 3. So it is like cos of 3 into pi by 6. Pi by 6 means 30 degree. Cos of 3 into pi by 6 is cos of 3 into 30 means cos 90. Cos 90 is 0, 1 or minus 1. It is a 0 na. So n is equal to 3 is absent. Are you getting the point? Similarly, you can check for n is equal to 9. Cos of 9 into pi by 6. You will get idea. Okay. Cos of 9 into pi by 6. That is 9 into 30. It is a 0. You can check for cos of 15 into pi by 6. It is a 0. So please keep it in mind. In the line voltage also, we are having a triple n harmonics are absent. Please be careful. In the expression, I have written here cos of n pi by 6. And I have put here 3. Okay, so simultaneously you can check. If you put here 3, it is like cos of 3 into pi by 6. Okay, so cos of 3 into 30, so it is cos 90, 0. Similarly, you can check remaining triple n harmonics. You will understand. Okay, so in the line voltages also, all the triple n harmonics are absent. Okay, so let me write here. In line voltages, in line voltage, all even and triple n harmonics are absent. Harmonics are absent, right? Whereas in pole voltage, all even harmonics are absent. Are you getting the point? And what about in a phase voltage? In phase voltage, all even and triple n na? In a phase voltage, let me write that also. In phase voltage, all even and triple n harmonics are absent. Right? Okay, so please keep it in mind. Today's this 3-phase is very important, right? Okay, so now if you are having any question, please ask. Right, we'll stop here for today. Tomorrow we'll be meeting at 2 p.m. Okay, so for tomorrow we'll be discussing about 120-degree conduction mode. After that, the pulse width modulation technique. Okay, and that will be for inverter case, that is AC to DC to AC converters. And next we'll be discussing a small chapter, that is a AC voltage controller. Okay, so hardly I think tomorrow we are having the session till 8:30, but probably we will finish around 6:30 or 7, right? Okay, so if you are having any question, please ask.
Hello, sir.
Hello.
Hi,
Hello,
yes,
sir.
please. Yes, please.
Sir, actually in the three-phase inverter, normally all are not recommended the RL circuit, sir. Actually, in the book it is also mentioned, actually not RL circuit, but there is some problems on RL load. Means we
Where?
always for R load, we are calculating for R load on. Means if a three-phase induction motor is connected, then how will we calculate this should be
What they have asked the question?
Actually, I am asking for that switching circuit. How the switch will be connected? There is a previous gate question actually. There is what type of for induction motor and delta connected capacitor
Please listen,
compensation.
This is your voltage source inverter.
Sir, current source.
No. This is the voltage source inverter. Na 3-phase inverter is also.
This is a voltage source inverter.
So in the voltage source inverter, whether the output voltage depends on the nature of the load.
That is only DC we are supplying, so we are getting that this type
No,
of.
my question is actually the thing is any load you can connect, the V0 waveform will be getting the same. Just like your single phase inverters, right?
Yes, sir.
Okay, here also you'll be getting the same thing. Okay, for V0 I am saying, right? And for V0 we are having the Fourier series expressions. Accordingly, you can write the current expressions.
What will the current waveform actually?
Current waveform will be like that. Whatever we discussed now, for if the load is L load, then it will be like a triangular type shape.
But in the book it is complicated, sir. Means it is unable to understand, sir. Actually, complete increasing. that for जो RL load.
Okay, RL load they have given. That should be the exponential function.
For somewhat it is exponential. Okay, okay.
Right? RL were having exponential, na? Here L load were having triangular.
Also, yes, sir. Actually, in a test series question, it is asking that what is, let's suppose that waveform is actually peaky nature for 2 VC by 3.
2.
VC
Your
interval.
voice is breaking. Audio is breaking.
Actually, for R load, if we are drawing the current waveform, then we will get highest means peaky current waveform at 2 VC by 3. That in from that we are getting in the for 2 VC by 3, that interval, the current will be in peaky nature. That you have said that exponential.
Okay, where they have given peaky wave?
Peaky means sir.
In transformer we are having peaky wave.
Sir.
In transformer we are having peaky wave, na? Okay. Yes. Generally, the thing is, if you check the previous question papers also, right? The only they have asked on the resistive load. But my suggestion is, any load you can connect, as this is the voltage source inverter, your output voltage nature will be same, right? It will not change. So once we know the Fourier series expression of the output voltage.
Yes, sir.
Just now we discussed. So accordingly, we can write the Fourier series expression of the current also, even though if they change the load.
Yes, sir. Means from RL circuit, we are dividing only Zn.
We can simplify, right?
Okay. Sir, in line voltages, this expression what you written right now.
In line?
Sir, this right now you wrote the statement that line voltages there will be no triple N harmonics and even harmonics.
Yes. Line voltage here, VAB. Sorry.
Sir, but again, VAB expression you have 135, no, sir. Then how can we say the triple N harmonics?
No. Why I have written 135? Because you can check na. In general, this expression is there cos of n pi by 6.
Okay, sir.
If you put 3 here, what will happen?
Okay, sir.
Cos of 3 pi by 6. So it will be 0, na?
Yes, sir.
So like this, for any triple N harmonic, you can check it will become 0, right?
Yes, sir. And sir, one more, sir, regarding this natural load commutation in this.
Okay, RLC.
Yes, sir.
Okay.
There, you mentioned that in order for maintaining the reverse voltage, the diode's forward voltage drop will give that what we say is a reverse voltage across SCR.
Yes.
Sir, but this like actually we do know that for a faster commutation, magnitude of reverse voltage is higher, then the commutation will be faster.
For faster commutation,
if the magnitude of this reverse voltage is high, then the rate at which these charges are removed from the top 2 layers will be faster.
Yes.
But again, this is only minus 0.7 volts, no, sir. It will take much more time.
No, it is not like that. It will take much more time. That's why we are using the factor of safety also, na? Even though the device turn off time is that much, but then also we are keeping some more time so that device should successfully turn off.
Okay, sir.
It is not like that the time is very high. It is not like in minutes or seconds. It is hardly in fraction of seconds, right?
All right, sir.
Right.
Good evening, sir.
Yes, good evening.
Sir,
Hello, sir.
Hi, yes, please.
Sir, in chopper. Hello.
In chopper, yes.
Sir, we have two commutation, no, sir. Voltage commutation and current commutation. Which we are using the practical or voltage or current, sir?
Which we are using in practical?
Yes, sir.
No, both are we are using voltage and current commutation. But the advantage is in the current commutation, suddenly a large reverse voltage is not getting experienced by the SCR because of that inductor.
Yes, sir.
But whereas in a voltage commutation, you can check suddenly a reverse high reverse voltage will be getting maintained across SCR.
Okay, sir. Means probably we are using mostly voltage commutation.
Yes.
Sir. Thank you, sir.
Okay.
Hello, sir.
hello, sir.
Yes, please.
Sir, 333F, sir.
333.
Yes, sir.
Okay, huh?
Sir, here, why there is phase shift between V01 and V02, sir?
Why there?
Why there is a phase gap of 5, sir?
Okay,
For
okay.
V.
This you are saying. This you are saying. Okay, okay.
Yes, sir.
The thing is, you can check. This is the circuitry we are having.
Yes, sir.
4 switches we are having. Which
Sir.
switch, when to turn on, is in my hand.
Yes, sir.
So I can turn on any switch at any time. So what they have done, during omega t is equal to 0 to pi. Okay, right?
Yes, sir.
It is like, in order to get V10 to be equal to Vs, right? So
Yes, sir.
what they have done, it is like V10, they have given Vs, right?
Yes, sir.
Okay, okay, it is not Vs by 2. Okay, okay, okay. Anything, anyway, it is like they have created a phase displacement of 5 radian here.
Yes, sir.
The same thing you will understand in the tomorrow's session. In order to reduce the harmonics,
Yes,
we are
sir.
having one method, that is a series connection of the inverters.
Okay, sir.
In that you will understand ki I can operate the switches, okay, as
Yes,
per
sir.
my desire,
Yes, sir.
right? So that's why it is not the big thing ki how they have got this waveform, right?
Sir, okay, sir. I thought it is due to capacitance, I thought, sir.
Because the thing is, our switches are, we are using, those are the fully controlled switches, na?
Yes, sir. Yes, sir.
We are turning it on at any instant we want, and we are turning it off at any instant. But whereas in the rectifier, it is like we were turning on as per our wish, but it was turning off as per the supply na nature.
Yes, sir.
Right. Okay. Okay.
Sir, 331F, sir.
331F. Okay.
Sir, can you explain why this angle you have taken, like, why
Minus.
this angle? Yes, sir.
Okay.
Minus not, sir. 43.2 only, why you have taken?
Okay, okay, okay. Because here we need to find by how much angle the current is leading to voltage.
Yes, sir.
So you can check. First thing is I have calculated the time TC.
Yes, sir.
TC means what? The circuit turn off time of thyristor.
Yes, sir.
So circuit turn off time of thyristor means, in this circuit, if you check, we have discussed here. Yes. If you check the waveform, that TC was like from when current becomes 0, na?
Yes, sir.
And
303, sir.
Yes, yes. 30.
3.
Yes, very good. No, 303.
Oh, yeah.
Yes, here it is.
Yes, sir.
300. Okay, okay. So from this point to this point, it is a TC, na?
Yes, sir.
So we have calculated this TC means this time we have calculated.
Yes, sir.
And corresponding to this time, after that, I have calculated the angle.
Yes, sir.
So from this angle, I got the information that you can check. This point indicates, or this corresponding to this TC angle is nothing but your current is leading to voltage by that much angle.
Yes, sir.
You can check na.
Yes.
This angle is theta, so therefore this angle is also theta, na?
Yes, sir. Yes, sir. Yes.
Right. So that's why we calculated the theta. And once we got the angle of leading, okay, between
Yes,
voltage and current, and from that I have used that formula, tan theta is equal to that expression.
Okay.
Right?
Sir, again, how here before T is equal to 0,
Huh.
how we got the current, sir, here? Means T is equal to 0 minus E.
No, this is only for continuous conduction.
Okay, sir.
Are you getting the
Continuous
point? Now you can check in a continuous conduction. You can check. It is like pi means somewhat here this point. Yes or no?
Yes, sir.
So from pi
Yes,
to
sir.
2 pi, whatever the waveform, this waveform will be copied here, na?
Yes.
That pi to 2 pi waveform will be appearing at 0 to minus pi, na?
Yes, sir.
0 to minus pi means negative, right? Same.
Okay, sir. Sir,
Okay.
sir, here you have said that capacitor will discharge, no, sir, in this RLC circuit.
Yes, yes, yes.
Sir, means inductor. Okay, sir. Okay.
Capacitor will discharge in the reverse case, na? Means reverse direction.
Hello, sir.
So that's why you can check here. S1, S2 on means capacitor charges, and through D1, D2 they are discharging. But whereas in the case of inductor, S1, S2 through S1, S2 inductor is charging, and through
Yes, sir.
D3 to inductor is storing energy, not charging, inductor is storing energy. and through D3, D4, it is releasing the energy. In
Yes,
the
sir,
case
yes,
of
sir.
inductor, while releasing the energy, current direction should be same. But in the case of capacitor, it is opposite, na?
Yes, sir, yes, sir. Sir, again, sir, in day before yesterday class, one problem is there for boost converter, no, sir. Means they're not, they have not given any switching frequency, sir.
Yes.
Sir, in that case, you have used that diode average current is equal to load average current, sir.
Yes, yes.
Sir, means, but there will be capacitor between those two, no, sir. Means current division will be happen, no, sir. How can we say that diode average current will be the load average current, sir?
No, but in that problem, if you check the capacitor, they have mentioned only C. Whether they have given the value.
No, sir.
So it is like a capacitor is highly inductive. Oh, sorry, high value of a capacitor is there.
Okay, sir. Then impedance
So
offered by
that's
it
why
is
the
zero.
current of the capacitor is neglected.
Okay, sir.
Right. So from that we got that answer. Okay.
Yes. Means you
Because they have not
neglected
given the frequency, so that's why we need to find in that way only.
Okay, sir. Means if they have given capacitance, there is no other method to find, sir.
No other method.
Okay,
If
sir.
they
We
could have
to,
given that the frequency, then we would have calculated by using that expression, right?
sir, if the C value is very high, then XC value will be very less, no, sir.
Okay, huh?
Sir, then it will be like short circuit, no, sir. It means we cannot neglect that current, no, sir.
Okay. But in this case here, please listen. If the capacitor value is high, means it is like capacitor is maintaining the constant voltage.
Yes, sir.
If capacitor is maintaining the constant voltage, means it is like capacitor has fully charged.
Okay, sir.
And now it is not allowing any current.
Oh, okay, sir.
So constant current, constant voltage, na capacitor means neither
Yes, sir.
capacitor is discharging, not it is charging.
Okay, sir.
So
It is
that's why
maintaining.
particularly in that branch, it is like a zero current.
Okay, sir. We have to think like that, sir.
Yes.
Okay, sir. Another one, sir. If the mode is discontinuous mode, we cannot use this formula, sir. IL average is equal to, in case of boost, I naught by 1 minus D.
IL average is equal to
I naught by 1 minus D, sir.
okay in the discontinuous mode.
Yes, sir.
Yes. We need to again derive that,
Okay, sir.
because in the discontinuous we have only derived the V0 average, na?
Yes, sir.
Right? But we can derive. Okay.
Okay, sir.
Again, that from ampere second balance equation and those things, right?
Oh, okay, sir. Okay, sir. Yes, sir. Thank you, sir.
Okay, yes. Yes, please, next.
Hello, sir.
Yes, please.
Sir, according to the Fourier series, so odd harmonics will be dominating and even harmonics will be zero, no, sir.
What are you saying? Yes.
Regarding harmonics, sir. Regarding harmonics,
Yes.
where harmonics are generating, sir, in the switches, sir.
Actually, the thing is, if you recall, in the power electronics, in the very first lecture, in the
Yes, sir.
disadvantages, I have mentioned one point, that is it adds the harmonics in the system, na?
Yes, sir.
Those harmonics are due to the switching of action of the switches, because we are turning on, turning off the switches, na?
Sir.
So due to that, the harmonics are getting added.
Means due to conduction loss like that, sir.
No, due to the switching only. You can check out in the case of rectifier itself. Okay, suppose if I turn on the switch, okay, at alpha equal to 0 degree,
Okay, sir.
then my suppose if the load is a resistive, and if I am turning on the switch at alpha equal to 0 degree, then what will happen? My source voltage waveform and the source current waveform both will be same, na?
Yes, sir.
So in that case, it is like your power factor will be good, right?
Yes.
So your current waveform is also purely sinusoidal type thing. But if
Yes,
you
sir.
check what we are doing, we are maintaining the alpha as a non-zero, na? So due to that
Yes, sir.
switching, it is like those harmonics are getting added into our system. Means our current waveform is a non-sinusoidal.
Okay, sir.
If your current waveform is sinusoidal, this is what we expect, na? if your voltage waveform or your current waveform is, in the case of inverter, it is like output voltage. In the case of rectifier, it is like a source current. Yes or no?
Yes, sir.
Generally in inverter, we expect ki output voltages should be sinusoidal, but we are not getting those.
Yes, sir.
This we are having the harmonics. Okay.
Okay, sir.
Right? And this is the one method with the help of switches we are getting it. Okay. And now how to improve how to reduce the harmonics, and for that, while doing the PG, you will understand we are having the multi-level inverters and those concepts. These are the basics actually. 120 degree, 1 degree. These are very basics. Okay. Apart from that, nowadays, if you check the research, we are having the multi-level inverters. Okay. In the multi-levels, we are getting the output in steps actually, more closer to the sinusoidal. Right.
Sir, deviating from the sinusoidal is the harmonics, sir.
Yes. Deviating from the sinusoidal is the harmonics.
Because of intermediate switching.
Yeah, because of the intermediate switching. But in this case, if you check, because here where the input is DC and we are operating the switches like this now, 120 and 180 degree conduction mode type thing. So that's why we are not getting the output even more closer to the sinusoidal.
Yes, sir.
Right? More closer your sinusoidal, more suppose if I am having the VAB waveform, which is more closer to the sinusoidal, the meaning is my VAB consists of lesser harmonics.
Okay, sir.
Right? Like that thing. If VAB is sinusoidal, then harmonics will be 0.
Yes, sir.
Right? But our main try is to get as close to a sinusoidal, na?
Okay, sir. And one more doubt, sir. So, in this lesson, we will teach about current source inverters also, sir.
Yes, definitely. Current source inverter also I will be teaching. Okay. In the current source inverter, only special case we are going to discuss, that is the capacitive load. Right?
Okay. Okay, thank you.
The thing is, in the voltage source inverter, we are having the voltage nature is like a square wave, na?
Yes,
the current source, you will be getting the current nature is like a square wave. You will understand tomorrow. Okay.
Sir, here why we did not calculate about power factor, sir?
Where?
Output in output we did not calculate about power factor, no, sir.
Okay. Here we have considered the resistive load.
Okay, sir.
Right. But if you want to find the power factor for the other load by considering the REL load also, okay, then we are having the Fourier series expression of the phase voltage waveform. From that, we need to write the phase current waveform.
Okay,
right?
sir.
From that, you can find the total power P and Q. P and S power. That is, we discussed now. If the voltage also consists of the third harmonic, then how to write? Okay. Means you need to write the S, that is the apparent power.
Yes,
and that real power divided by apparent power means your overall power factor.
Okay, sir. In problems, they will ask about power factor or not, sir?
No, they will not ask. They will not ask. Right?
Okay, thank you, sir.
Okay. Yes, next.
Hello, sir.
Yes, please.
331F, sir.
331.
Yes, sir.
Okay. Yes.
Here minus will be, how will become negative, sir?
Okay.
Minus 43 point.
Yes. Listen here. While calculating the angle by using this expression tan inverse of XL minus XC by R, na?
Yes, sir.
The lagging angle, if the angle is lagging, then it is like a positive.
Okay, sir.
Angle is leading means it is a negative. Now please try to understand why I am saying it is a positive negative, because it is tan inverse of this thing, na? XL minus XC.
Yes, sir.
If XL is greater than XC, what will happen? Your resultant current will lag the voltage, na?
Yes, sir.
So if the current will lag, XL is greater than XC means overall circuit will be like a RL circuit.
Yes, sir.
So current lags means what? You will be getting the angle is like a positive. You can check na tan inverse of, suppose, for example, suppose R is equal to 2 ohm. Consider XL is equal to 5 ohm and XC is equal to 3 ohm. And find the tan inverse of that angle. You will be getting the positive angle. Similarly, now you can check XC greater than XL. For example, suppose XC is equal to 5 ohm, XL is equal to 3 ohm and R is equal to 2 ohm. And find the angle. If XC greater than XL, then the angle you will be getting negative. So XC greater than XL, the meaning is your circuit is like a RC circuit. Capacitive effect is more, na?
Yes,
That's
sir.
why current is leading. So that's why for leading, the negative angle should be considered. Okay.
Okay, sir. 337 F, sir.
337. Okay. This one.
No, sir.
Then
A and C is positive interval, sir. First interval.
in this only.
No, sir. No.
Or which slide you are saying?
I think 339, sir.
339. This one.
Okay. Sir, yesterday one problem, sir. No, sir. That one.
Which one?
Yesterday chopper, sir.
Which problem?
Last to second one, sir. Before type of chopper. Types of chopper. Last one. Conduction time of period T2 plus T3 minus T2.
Okay. That thing. Okay.
VC waveform, sir.
Whether it is there or not, let me check first. Okay. For this one, yes, please tell me what is your doubt, because the solution is not there in this sheet. Okay.
Okay, sir.
Please
VC
ask
waveform,
me,
sir.
ask me. Which waveform?
VC voltage across capacitor across voltage, sir.
Voltage across capacitor.
T2 plus T3 minus T2. But how will be write on T2 will be T Anna, sir.
Yes, correct.
T3 minus T2 will be 2 TC.
2 times TC.
How will be right, sir?
Because you can check between T2 to T3.
My doubt that one not, sir. T2, T3 minus T2, okay, sir. But T2 plus, how will become T2 plus, sir, again?
Okay, we wrote it as a T2 plus T2 minus T3, na?
No, sir, T3 minus T2.
Yes, T3 minus T2, correct. We wrote it as like this, na? T3 minus T2, na?
Yes, sir.
Okay. Now, in this case, means if you check T2 means it is like this, na? 0. Here it is T1, here it is T2, here it is T3. And I think the VC waveform, na? It will be
Okay.
somewhat like this. From here it is a cosinusoidal, na? After that, it is constant,
Yes, sir.
right? And after that, it is changing like this, na?
Linear.
This type of waveform. Okay.
Yes, sir.
And this time we indicated as a TC, na?
Yes, sir.
Okay. Then now, please let me know your doubt.
Conduction time period T3 minus T2, sir.
Conduction time period.
Time period.
Total or yes, T1 you are saying?
Yes, sir.
T1 is T2.
Okay.
Still, which instant your thyristor T1 is in on state? That is T1 they have given, na?
T2.
And if you check during this interval, IC is negative, na?
Yes, sir.
Corresponding to T2, what is the IT1? IT1 is 0 at T2. Please check.
Yes, sir.
Yes or no? IT1 waveform is like this. IT1 waveform, let me, yes, represent here. This is IT1. Till this point to T2, it is positive, na? It is voltage commutation circuit, right? So at this instant,
Yes.
it suddenly fall to 0. Before this, at the starting, that is 0 to T1, I think it will be like this. This type of waveform, na?
Yes, sir.
At this instant, thyristor T1 current becomes 0. Okay. But
Yes, sir.
this is nothing but your on time T1 of the thyristor. Okay, means thyristor
Okay.
conduction time is this one. But they ask the effective on period, na?
Yes, sir.
Effective on period means we need to consider till the instant our V0 is a positive, V0 is non-zero.
Yes, sir.
So if you check the V0 waveform, till T3 V0 waveform is non-zero, na?
Yes, sir.
It is like from 0 to T2 it is a Vs only. T2 to T3 it is like a 2 Vs to 2 Vs to 0, it is decreasing, na?
Yes, sir.
Effective on period is 0 to T3 actually.
Okay, sir.
So that T3 I have written like T2 plus T3 minus T2, na?
T2 plus T3 minus T2.
Right? So this is T1 and T3 minus T2 is this. If this is TC, so remaining is also TC, na?
Okay, sir.
That's why it is 2 TC.
Okay, sir.
Right? Because it is a linear, na? It is linear. So for changing the Vs from this point to this point, how much time it is taken? The same time it will take to change from this point to this point also. Because it is linear, right?
Yes, sir.
That's why it is TC plus TC. Okay?
Okay, sir.
Right. Yes, next.
Hello, sir.
Yes, please.
Sir, I have asked about the thermal stability. Can you tell me tomorrow?
No, I will. Yes, I am having. Tomorrow I will finish all your doubts. Okay.
Yes, sir. Yes.
Yes. There's that one and one more yesterday is that the form factor someone asked me. Okay. Right.
Sir, thank you.
Okay. Yes, next.
Sir, good evening, sir.
Good evening. Please.
Sir, in 330 slide. 330, sir, 330.
330. Okay.
Yes, sir, 330.
Yes. This one?
Sir, how to find the angle, sir?
Okay. The thing is, you can check that time duration they have given. That is a capital T, na?
Oh, yes, sir.
That here it is. Time duration you can check. That is periodicity, na? 0.2 millisecond. Periodicity means one complete cycle, na? AC.
Yes, sir, one complete.
So corresponding to one AC cycle, we are having angle is 360 degrees.
Sir?
We are having angle is 360 degree, na? Corresponding to one AC cycle.
Yes, sir, one cycle, 360 degree.
Right? So for 0.2 millisecond, it is a 360 degree.
Okay,
Then for
sir.
this time, how much? That's why I have represented it as a X.
Okay, sir. Okay.
So simply take the cross multiplication. It is like 360 into TC divided by T means X, na?
Yes, sir. Okay.
The same thing I have written here. Okay.
Yes, sir. Sir, in 180 degree mode, at a time we have, sir, I don't get that point, sir. At a time you conducting three methods, sir. Between 0 to. Sir, in 180 degree conduction, 0
Three phase
to
inverter you are asking. Three phase inverter.
Yes, sir. Three phase inverter.
In that, where is your doubt?
Sir, I don't get that point, sir. You have told that it is conducting at a time 3 devices.
Yes, 3 switches will be in a conduction mode at a time.
Yes, sir.
You can check the circuit diagram here. Yes. Okay. So we're having the operation table like this, na? So
Yes, sir.
according to this operation table, we are operating the switches.
Okay,
right?
sir.
Means during
Yes, sir.
first 60 degree, we are operating S5, S6, S1.
Okay, sir.
These switches will be in a conduction mode. During second interval, S6, S1, S2. Means we are turning off S5 at the end of this interval.
Okay, sir.
And how we are turning it off? If those are the thyristors, we are using the forced commutation. If those are the BJTs, then I am reducing the base current. If those are the MOSFETs, I am reducing the VGS, right?
Okay, sir.
So like this, 3 switches will be in a conduction mode at a time. Okay.
Okay, yes, sir.
And from this, we have drawn this equivalent circuit. From here, you can check 3 switches. So accordingly, the respective phases of the load will be connecting to the positive plate or the negative plate of the supply, and from that for each interval we have drawn the circuit like this. This is for third interval,
Okay.
and accordingly you can find. Okay.
Okay, sir.
Right.
Yes.
Okay. Yes, next.
Hello, sir.
Yes, please.
Sir, for the Fourier series calculation of Cauchy square wave.
Okay.
Sir, we shifted it by angle 30 degree, right? For odd, it seems to be odd signal.
Yes.
Sir, if we shifted it by minus 60 degree or plus 300 degree, it will be even signal, right?
If we shifting by 60 degree, you are saying?
Minus 60 degree or plus 300.
Minus 60 means at which side you are saying? Left side, right side?
To left side, sir.
Left side by 60 degree, you are saying?
Yes, sir. Yes, sir.
Okay.
It will become even signal.
Okay. Just a minute, let me check. By 60 degree, you are saying. Okay. So from 2 pi, we are switching by 50 degree. Means this will be like at 2 pi by 3, it will be starting, na? This negative
Yes,
will
sir.
be starting here.
Yes, yes.
And okay, this will be here. Okay, the
Then means this
negative
VS
pulse will
is,
be from 2.
yeah,
Okay.
yeah. Out of VS is 120 degree. It only 60 degree in right side and 60 degree in left side.
Okay. Whether it will
And
be
we can also calculate it using event signal like that.
Okay. Yes. Let me. Yes, please. What is your doubt?
Sir, if it is shifted by left side 60 degree, it became event signal.
Okay.
What about the Fourier series calculation of that? It will
The
become
thing
same
is,
as this.
yeah, at the end, the result you will be getting is the same only.
Okay.
But the thing is, why I am preferring the odd signal, because here for odd signals we know AN is 0, na?
Yes, sir.
So that's why only thing is we need to reduce the calculations. Okay.
Okay.
That's why I'm shifting first, right?
Okay, sir. One more doubt.
Otherwise, without shifting also we can calculate the VAB Fourier series. But
Yes,
we need
yes.
to find the AN value. We need to find the BN value also, na?
Okay.
Anyways, BN we are calculating. Okay, but
Yes,
AN, that will be the additional task.
Okay,
So in
it will
order to
become
reduce
easier.
that, yes. To reduce
Sir,
the
one more doubt.
calculations.
Sir, in harmonic factor, while calculation, formula we given as V0 and RMS divided by V0 and RMS.
V0 n RMS divided by V0 1 RMS.
1 RMS. It will become 1 by n, right, sir?
It will become 1 by n. In our case.
Yes, that is the inverter in half and full bridge.
That is in our case it will become. But if you check in general way, those formulas are the general, na?
Yes,
because
sir.
for a single phase half bridge, single phase full bridge, you are getting the relation like 1 by 3 and those things, na? But for
Okay.
other waveforms, suppose if the even signals are also present, even harmonics are also present, then in that case that will be different, na?
Okay, sir.
Right?
Okay. Thank you, sir.
Okay.
Hello, sir.
Yes,
Hello, sir.
please. Yes.
Sir, you have said that in case of rectifiers, the distortion factor is IS1 RMS by IS RMS, but here distortion factor is different, sir.
Where?
In case of rectifiers, you have said for calculation of input power factor, you have said that distortion factor is equal to IS1 RMS by IS RMS.
Okay.
But here distortion factor formula is different to that one, sir.
Yes, let me check. We discussed before numericals, no?
Yes, sir.
Yes. Here.
Yes, sir.
No,
Sorry.
that distortion factor, whatever you are saying, okay?
Yes, sir.
That was like, what was that formula?
IS1 RMS by IS RMS, sir. fundamental
that was
RMS
the distortion factor of your overall waveform.
Yes, sir.
This is the distortion factor of that respective harmonic.
Means what is the difference between both, sir?
No. The thing is that was for including all the harmonics.
Yes, sir.
This one is for individual harmonic. From
Okay,
this,
sir.
if I want to find your distortion factor of the respective waveform is including all the harmonics, na?
Yes, sir.
Then I need to find the distortion factor of respective harmonics, and then I need to add those, na? And accordingly, I will be getting whatever the expression we derived there, we used there, the same expression will be there. But as long as your inverter questions are considered,
Yes,
generally
sir.
they ask for the respective harmonic. So that's why we have given this formula.
Okay, sir.
Right? For
But you-
overall waveform, if you want, then you can use that formula also, right?
Okay, sir. For overall waveform, we can use that formula, sir.
Yes. And this is
Okay,
for
sir.
individual harmonic,
Okay, sir.
right? Okay. Sir, can you please contact to the schedule manager once and kind ask? No, actually he has already scheduled the next subject, that is your electronics measurement part. Okay, electronics measurement. Yes, next. Okay. ठीक है. So stop
Sir,
here.
Sir, you know that,
Yes.
sir, normally, sir, for next schedule also we have two subjects, sir.
One.
Sir, for next schedule also we are having two subjects, sir. Only one, sir.
That actually I am not sure. Okay.
Oh, okay, sir.
Okay. Please discuss with the office people.
Okay,
Right?
sir.
Okay. Great. Yes. Thank you. Thanks to all of you. So tomorrow we'll be finishing the power electronics, right? Right. Thank you.